A silent voyager, perhaps no wider than a city block, is drifting through the vast emptiness of space, its path an elegant sweeping curve that betrays an origin far beyond the gravitational reach of our sun. It is a ghost from another star system, a fleeting visitor on a one-way journey through our cosmic neighborhood. We call it 3I Atlas, a name that is both a scientific designation and a story in itself. Unlike the planet's asteroids and comets that are bound to our sun in an eternal looping dance, this object is a true wanderer, its trajectory a hyperbolic arc that guarantees it will pass through our solar system only once before vanishing back into the interstellar dark from which it came. Its brief passage is an extraordinary and fleeting gift, a chance for humanity to study a pristine piece of another world, a sample of the raw materials that build planets around a distant unknown star. It is a time capsule frozen for millions or perhaps billions of years, carrying the chemical fingerprints of its alien birthplace. And in its silent, icy heart, it may hold the answer to one of the deepest questions we have ever asked: are the building blocks of life unique to our small corner of the galaxy, or are they scattered like seeds upon a cosmic wind, waiting for a welcoming shore? The discovery of 3I Atlas was a moment of pure serendipity, a testament to the power of looking for one thing and finding something far stranger. On the 12th of December 2019, an automated telescope system in Hawaii, part of the Asteroid Terrestrial Impact Last Alert System, or ATLAS, flagged a faint, fast-moving point of light. The primary mission of the ATLAS survey, funded by NASA's Planetary Defense Coordination Office, is to scan the skies for near-Earth objects, the asteroids and comets that could pose a potential threat to our planet. It is a sentinel, a sleepless guardian watching for danger. But on that night, it found not a threat, but a mystery. At first, the object was catalogued as just another comet, its faint hazy appearance typical of an icy body warming as it approaches the sun. But as more observations were made over the following days and weeks, a startling truth began to emerge from the data. Its orbit was not the familiar closed ellipse of a solar system comet. It was an open hyperbolic curve. The calculations, when run backward in time, confirmed a stunning conclusion: this object was not from around here. It had arrived from the vast dark expanse of interstellar space. Detecting such visitors is an incredibly difficult task. They are typically small, dark, and moving at astonishing speeds, their brief passage through our solar system a fleeting whisper in the cosmic dark. The fact that the ATLAS survey, with its wide-field but relatively modest telescopes, spotted it at all was a remarkable achievement. Once astronomers around the world realized the significance of the discovery, a global effort was mobilized. Telescopes, large and small on the ground and in space, turned their gaze toward this strange new visitor, racing against time to capture every possible photon of light before it disappeared forever. Every detail mattered: its brightness, its color, its rate of rotation, the chemical composition of the faint halo of gas and dust that surrounded it. Each of these was a clue, a piece of a puzzle that could reveal the nature of its mysterious origin. Early observations showed that unlike the first confirmed interstellar visitor, 1I Oumuamua, which had been mysteriously inert and tailless, 3I Atlas was active. It had developed a faint coma as it warmed near the sun, a sign that it was releasing volatile ices from its surface. In this, it resembled the second interstellar visitor, 2I Borisov, though its activity was far more subdued. The timing of the discovery was a stroke of scientific luck. 3I Atlas was spotted before it reached its closest point to the sun, its perihelion. This gave astronomers a rare and precious opportunity to observe it during its approach at its peak brightness and then as it receded back into the darkness. This was a luxury they did not have with Oumuamua, which was only discovered as it was already on its way out of the solar system, a missed opportunity that has haunted astronomers ever since. During its perihelion passage in late December of 2019, 3I Atlas became just bright enough for medium-sized telescopes to gather spectroscopic data to break its faint reflected light into a rainbow of chemical signatures. It was never visible to the naked eye, a ghost that revealed itself only to our most sensitive electronic eyes. By early 2020, it was already fading rapidly, its brief moment in the sun over its long journey back into the interstellar void begun. The timeline of discovery is everything for these cosmic messengers. They spend only a few short months within the observational reach of our telescopes. To miss that brief window is to lose a priceless opportunity to study pristine, untouched material from another star system, a free sample from a world we cannot yet visit ourselves. And by carefully tracking its trajectory, by reconstructing the path that brought it to our doorstep, scientists hope to answer the most tantalizing question of all: where did it come from? After being violently ejected from its home system, it likely drifted through the galaxy for millions of years, a lonely traveler in the dark. Its precise hyperbolic path is a fossil record of that journey, and in its subtle curves and angles may lie the clues that could point us back to the distant stellar nursery that launched it on its incredible silent voyage. The name 3I Atlas is more than just a label. It is a compact story, a scientific classification that carries within it a record of discovery and a declaration of the object's extraordinary nature. Each part of its designation tells us something crucial: where it stands in the history of exploration, how it is classified, and how it is fundamentally different from the countless other small bodies that populate our solar system. The I is the most important letter in its name. Unlike the designations used for ordinary comets or asteroids, this single letter is a brand, a mark that sets this object apart as something truly rare and profound, an interstellar object, a traveler born in the crucible of a distant star system, a wanderer that roams freely across the galaxy, unbound by the gravity of any single sun. This convention, the use of I for interstellar, is a very recent invention in the long history of astronomy. Before 2017, no confirmed interstellar visitors had ever been recorded, so there was simply no need for a naming system to classify them. That all changed with the electrifying discovery of Oumuamua. Once astronomers confirmed its unbound hyperbolic path, the International Astronomical Union, the official body responsible for naming celestial objects, recognized that these cosmic travelers from beyond our solar system deserved their own unique classification. And so the I designation was born. The numbers that precede it are assigned in chronological order of discovery. Oumuamua as the first received the designation 1I. The second, the active comet Borisov, discovered in 2019, was assigned 2I. And this visitor, 3I Atlas, now holds the official title of the third confirmed interstellar object ever observed by humanity. This simple sequential numbering system is creating a historic catalog, a small but rapidly growing collection of alien visitors that have been caught in the act of passing through our cosmic home. The second part of the name Atlas is a tribute to the survey that made the discovery possible. It is a long-standing tradition in astronomy to honor the team or the technology that first spots a new object by including its name in the official designation. This not only gives credit where it is due, but also provides a convenient way for scientists and the public to link an object to its discovery story. In this case, the Atlas system not only found the object, but did so early enough in its journey to allow for a comprehensive campaign of follow-up observations from telescopes around the world, making the inclusion of its name even more meaningful. Why is the I designation so scientifically important? Because it signals a fundamental difference in origin and history. Ordinary comets, which are born in our solar system's icy reservoirs, are labeled with a C. Asteroids are typically given a number. But interstellar objects are cosmic time capsules of a completely different order. They carry materials that were forged in an alien star system shaped by physical and chemical processes that were entirely independent of our own. The I instantly tells a scientist that they are studying a piece of another world, a sample that has traveled across the vastness of interstellar space to reach us. This designation also carries with it a palpable sense of scientific excitement. Each new interstellar visitor is a rare and precious opportunity to study the process of planet formation in other star systems. While our spacecraft can, with great effort and time, visit a few objects within our own solar system, these interstellar travelers come to us bringing with them a treasure trove of information. They carry untouched ices, ancient dust, and possibly even complex organic molecules, the building blocks of life. By studying their chemical fingerprints, we can learn about the diversity of planetary systems across the Milky Way and begin to answer the question of how common or rare our own solar system might be. The name of 3I Atlas also reflects the rapid acceleration of this new field of astronomy. Before 2017, the number of confirmed interstellar objects was 0. Just a few years later, we have 3. This may seem like a small number, but it suggests that such cosmic travelers are far more common than we ever believed. Previous generations of astronomical surveys were simply not sensitive enough to detect them. They are too small, too faint, and too fast. The arrival of 3Y Atlas is a sign that we are entering a new era of discovery. With the next generation of powerful wide-field telescopes like the Vera C. Rubin Observatory and its legacy survey of space and time, we may soon be uncovering dozens, perhaps even hundreds of these interstellar visitors every year. For scientists, this growing catalog of interstellar objects is a new window onto the galaxy. In the future, astronomers will look back at 1I, 2I, and 3I as the pioneers, the first chapter in a completely new story of galactic exploration. Each number is more than just a catalog entry. It is a milestone, a marker of humanity's expanding awareness of our place in a galaxy that is far more interconnected and far more dynamic than we ever imagined. The name 3I Atlas is a record of a single discovery, but it is also a promise of the countless discoveries that are yet to come. Every interstellar object is a cosmic detective story, its path through space, a trail of clues that points back to a mysterious and unknown origin. For 3I Atlas astronomers are in a race against time to decode this story, to reconstruct the long and lonely journey that brought this extraordinary visitor to our solar system before it disappears forever. The central mystery is its birthplace. If scientists can determine where it came from, or even just narrow down the region of the Milky Way it once called home, they could unlock profound secrets about the formation of other planetary systems and the ancient history of our galaxy. The investigation begins with the painstaking process of orbital reconstruction. The object's unusual hyperbolic trajectory is the primary piece of evidence. By tracing this open curve backward in time, scientists can estimate the direction from which it entered our solar system. This gives them a starting point, a broad patch of the sky from which the object appears to have emerged. However, pinpointing a single parent star is a task of almost unimaginable difficulty. Interstellar objects can drift through space for millions, sometimes even billions of years. Over these vast timescales, even the tiniest gravitational nudges from passing stars, giant molecular clouds, or other unseen objects can significantly alter their trajectories. It is like trying to trace the path of a single grain of sand in a storm. Current models suggest that 3I Atlas may have originated in the general direction of the constellations Carina or Scorpius. These regions of the sky are rich with stellar nurseries, vast, turbulent clouds of gas and dust, where new stars and planets are actively being born. These are the most likely environments for an object like 3I Atlas to be created and then ejected. During the chaotic early stages of planetary system formation, gravitational interactions between newly formed planets, especially giant ones, can act as powerful slingshots, hurling smaller comets, asteroids, and other icy bodies out of their home systems with enough speed to escape into interstellar space. Once ejected, these objects become true galactic wanderers, their paths shaped by the cumulative gravitational influence of the entire galaxy. For 3I Atlas to have reached our solar system, it may have been traveling for tens of millions of years, a silent and frozen refugee from a long-forgotten planetary birth. Unlike the comets that belong to our solar system, which are bound to the sun in predictable repeating orbits, these interstellar travelers roam freely, their paths a random walk through the star fields of the Milky Way. Some computer simulations even suggest that before arriving here, 3I Atlas may have passed through other star systems, each close encounter subtly warming its surface or altering its trajectory, leaving behind faint chemical and physical fingerprints that astronomers are now trying to decipher. Tracking its exact origin is further complicated by the fact that the galaxy itself is a dynamic, evolving system. Stars are not fixed points of light. They drift. They orbit the galactic center at different speeds, and their paths are constantly being perturbed by the gravity of their neighbors. To rewind the journey of 3I Atlas over tens of millions of years requires not just knowing its current motion with perfect precision, but also having a perfect map of the past positions and motions of every star it might have encountered. This is a task that is currently beyond our capabilities. The further back in time we try to trace its path, the larger the uncertainties become. Most interstellar objects are thought to be the casualties of planetary ejection events. In young, unstable systems, giant planets like our own Jupiter often migrate their orbits, shifting and sweeping through the protoplanetary disk, scattering smaller bodies in their wake. Some of this debris may be thrown violently into interstellar space, becoming cosmic exiles. 3I Atlas might be a fragment of a shattered exoplanet or a pristine leftover piece of a young system's building materials. Its composition offers additional clues to its birthplace. Its icy, volatile, rich nature, confirmed by early spectroscopic observations, suggests that it formed in the frigid outer regions of its home system, a place analogous to our own Kuiper Belt or Oort cloud. If it is particularly rich in carbon monoxide ice, as some data suggests, it may have formed in an even colder environment, perhaps around a star that is cooler and dimmer than our Sun. Comparing its precise chemical makeup to that of Oumuamua and Borisov is crucial. If these visitors share a common chemical signature, it might suggest they originated from a similar type of stellar nursery. If they are all radically different, it would point to a wide diversity in the chemical environments where planets form across our galaxy. The hyperbolic orbit of 3I Atlas is the clearest and most unambiguous proof that it is not from our solar system. An object's orbit is defined by a number called its eccentricity. An eccentricity of 0 is a perfect circle. A value between 0 and 1 is an ellipse, a closed path that will eventually repeat. An eccentricity of exactly 1 is a parabola, the borderline case for an object that just barely has enough energy to escape a star's gravity. And an eccentricity greater than 1 is a hyperbola, an open, unbound path that guarantees a single fleeting visit. For 3I Atlas astronomers measured an orbital eccentricity that was significantly greater than 1, leaving no doubt that it was a true cosmic wanderer. Its speed tells the same story. Long before it ever felt the gravitational pull of our Sun 3I Atlas was already hurtling through interstellar space at a speed of tens of kilometers per second, far too fast to be a native comet from our solar system, even one nudged inward from the most distant reaches of the Oort cloud. As it approached the Sun, its speed increased, but even after accounting for this gravitational acceleration, its outbound speed remains far above the Sun's escape velocity. It was never gravitationally bound to our star. Studying its orbit does more than just confirm its alien origin. It offers clues about the violence of the event that ejected it. A higher excess velocity implies a more energetic ejection, perhaps from a close encounter with a massive planet or a chaotic interaction in a dense star cluster. The precise shape of its hyperbolic path is a fossil relic of that dramatic formative event, preserved for millions of years as it journeyed through the galactic dark. Its motion also differs in fascinating ways from the two interstellar objects discovered before it. Oumuamua's high excess speed and unusual tumbling rotation set it apart. Borisov behaved more like a classic active comet. 3. I-Atlas seems to be a hybrid, its speed resembling Oumuamua's, but its faint cometary activity more like Borisov's. This growing variety is giving astronomers their first small but steadily expanding sample of interstellar visitors, hinting that such objects come from a wide range of star systems and are created through a multitude of different physical processes. The mystery of its origin remains a tantalizing puzzle that connects this one small icy visitor to the grand sweeping story of galactic evolution and the birth of worlds. One of the most immediate and telling signs that 3Y Atlas is not a native of our solar system is its incredible speed. Objects that are born within our sun's gravitational family are by definition bound to it. They may travel on long looping orbits that take them far into the outer solar system, but they rarely if ever achieve the velocities needed to break free from the sun's gravitational grip entirely. 3I Atlas, however, arrived with more than enough energy to do just that. Its motion tells a story of a violent past, a dramatic ejection from another star system, and a long, high-speed journey across the void. Even before it entered the sphere of our sun's influence, 3I Atlas was already hurtling through interstellar space at a speed of roughly 26 to 30 kilometers per second relative to the sun. To put that in perspective, Voyager 1, one of the fastest spacecraft ever launched by humanity, is currently traveling at about 17 kilometers per second. The comets that originate in our own solar system, even those from the most distant Oort cloud, typically drift at speeds of only a few kilometers per second when they are far from the sun. The defining characteristic of this interstellar visitor is its hyperbolic excess velocity, the speed it will retain even after it has completely left our sun's gravitational influence and is once again coasting through interstellar space. This is the unmistakable signature of a traveler that is truly unbound, a cosmic nomad with no home and no intention of ever returning. As it drew closer to the sun. 3. I-Atlas accelerated under the sun's gravity, its speed increasing as it fell deeper into our star's gravitational well. At its closest approach, its perihelion estimates suggest that it was traveling at an astonishing speed of over 60 kilometers per second, racing through the inner solar system before being slung back outward. Once it has receded far beyond the orbit of Neptune, it will have returned to its original interstellar cruising speed, silently continuing its endless journey through the galaxy. But why is this speed so important? The answer lies in the physics of energy. Objects that form within a solar system are born with a certain amount of orbital energy, a value that is tied to the gravity of their parent star. They are trapped. While their speeds may increase and decrease as they move along their elliptical orbits, they remain fundamentally constrained by the sun's pull. 3. I-Atlas, however, arrived with a huge surplus of kinetic energy, far more than any gravitational interaction within our solar system could have imparted to it. This excess energy is the indelible mark of its violent birth, the leftover momentum from the powerful event that ejected it from its home star system. Astronomers believe that most of these interstellar wanderers are born during the chaotic early phases of planet formation. In young newly formed systems, massive planets like gas giants often act as cosmic slingshots. Their immense gravity can capture smaller rocky or icy bodies like comets and asteroids and fling them outward with incredible force. Some of these objects are hurled out with enough speed to achieve escape velocity to break free from their parent star's gravity and begin a new life as interstellar travelers. The extraordinary speed of 3Y Atlas is a testament to the power of these gravitational interactions. Its speed also provides a rough sense of the duration of its journey. Traveling at 26 to 30 kilometers per second, it would take millions or even tens of millions of years to traverse the vast distances between star systems. It is highly likely that 3Y Atlas has been wandering the galaxy since the very early days of its home system, a frozen relic of a planetary birth that occurred long ago and far away. There is a strong possibility that it has encountered multiple other star systems along its way, each gravitational flyby subtly altering its course and speed, guiding it on the long random walk that eventually brought it to our cosmic doorstep. Compared to the other two interstellar objects discovered before it, 3Y Atlas occupies an interesting middle ground in terms of its speed. Oumuamua entered our solar system at a similar speed, about 26 kilometers per second. Comet Borisov was slightly faster at roughly 32 kilometers per second. All three share these exceptionally high velocities, confirming that interstellar objects are typically ejected violently and move fast enough to roam freely between the stars. Their rapid transit also explains why they are so difficult to observe. They spend only a very brief window of time within the reach of our telescopes, zooming through the solar system in just a few months. By the time astronomers can confirm their interstellar nature, they are often already receding and fading from view. For 3I Atlas. Its discovery, just before it reached its closest point to the Sun, was a stroke of incredible luck, giving scientists a slightly longer, though still frustratingly brief opportunity to study it. Even so, it brightened and then dimmed with astonishing rapidity, disappearing from the view of most telescopes within a single year. The sheer speed of 3I Atlas also raises a tantalizing and futuristic question. Could we ever send a spacecraft to intercept such an object? With our current propulsion technology, the answer is a definitive no. To catch up with and match the velocity of an interstellar visitor moving at tens of kilometers per second would require a mission with an energy budget and a level of precision that is far beyond our current capabilities. However, such missions may become feasible in the distant future, especially if we can develop new propulsion systems and if next-generation sky surveys can detect these travelers years in advance, giving us enough time to plan and launch a high-speed robotic interceptor. For now, we are left to watch these messengers from other worlds as they flash past their incredible speed, a constant reminder of the vast, dynamic, and interconnected nature of our galaxy. The Atlas Project, the astronomical survey that first spotted 3Y Atlas, is a remarkable testament to the power of systematic wide-field sky observation. Developed by the University of Hawaii and funded by NASA, its primary mission is a sober and vital one: planetary defense. Its network of telescopes is designed to scan the entire night sky night after night, searching for near-Earth objects that could one day pose a threat to our planet. But in its tireless vigil, it has unintentionally become one of our most powerful tools for finding something entirely different: visitors from other star systems. The strength of the Atlas survey lies not in the size of its telescopes, but in their efficiency and speed. It uses relatively small, wide-field Schmidt telescopes instruments that are specifically designed to image large swaths of the sky at once. While they cannot see as deeply or in as much detail as giant observatories, they can cover a huge amount of celestial real estate in a very short amount of time. The current Atlas network consists of 4 such telescopes, 2 in Hawaii on the volcanic peaks of Mauna Loa and Haleakala, and 2 in the southern hemisphere, 1 in Chile and another in South Africa. This global distribution allows the survey to monitor the entire dark sky. Each of these robotic telescopes sweeps the heavens multiple times each night, capturing a series of images of the same patch of sky. Sophisticated software then compares these images, automatically flagging any point of light that has moved against the fixed backdrop of the stars. Most of the time, these moving objects are known asteroids or comets, but occasionally something extraordinary appears. That is exactly what happened on that fateful night in December of 2019. The Atlas system detected a faint object that was moving slightly faster than a typical comet. Initially, it was given a provisional designation C2019Y4, assuming it was an ordinary long-period comet from the outer reaches of our solar system. But as more observations were collected and its orbit was refined, something unusual became clear. The numbers didn't add up. The calculations pointed to a hyperbolic path, an orbit with an eccentricity greater than 1. This immediately set off alarms in the astronomical community. Hyperbolic orbits are the calling card of interstellar objects. Over the following weeks, careful analysis confirmed the astonishing truth: this was not a comet from our solar system. It was a visitor from the stars, only the third confirmed object of its kind ever detected. The timing of the discovery made it even more extraordinary. Both Oumuamua and Borisov had been spotted relatively late in their journeys through our solar system. Oumuamua in particular was only seen after it had already passed the Sun and was speeding away. In contrast, Atlas detected 3-1 Atlas before it reached its closest approach, giving astronomers precious additional weeks to study it while it was still brightening. This early detection was a direct result of the Atlas survey's design. By repeatedly scanning the entire visible sky every 2 nights, it is perfectly suited for catching these fast-moving transient objects before they fade from view. Once Atlas had flagged the unusual object and its interstellar nature was confirmed, observatories around the world sprang into action. This international collaboration, coordinated through the Minor Planet Center, allowed for a continuous stream of observations with telescopes in different time zones picking up the object as the Earth rotated. This global effort, which included some of the world's most powerful instruments, would likely never have happened without the initial crucial detection by the relatively modest telescopes of the Atlas survey. The discovery of 3Y Atlas also highlighted the incredible progress that has been made in sky survey technology in just a few short years. Before 2017, no interstellar objects had ever been confirmed, not because they weren't there, but because our tools were not good enough to find them. These visitors are small, faint, and incredibly fast, making them all but invisible to older, less systematic surveys. Atlas's success is a sign that we are entering a new era, an era in which the detection of these cosmic travelers may become a regular occurrence. The next generation of surveys, particularly the Legacy Survey of Space and Time at the Vera C. Rubin Observatory, will take this capability to a whole new level. While Atlas can detect an object like 3Y Atlas, the Rubin Observatory, with its enormous 8.4-meter mirror and its gigantic 3.2 gigapixel camera, will be able to detect objects that are far fainter and moving even faster. It is expected to discover not just 1 or 2 interstellar visitors per year, but potentially dozens. It will create a veritable flood of data, transforming this new field of astronomy from one of rare serendipitous discoveries to one of systematic statistical study. But for now, the discovery of 3I Atlas stands as a landmark achievement, a beautiful and unexpected gift from a system that was designed to protect us from danger, but ended up opening a new window onto the wonders of the galaxy. To decipher the story of a distant silent traveler like 3Y Atlas, astronomers must become cosmic detectives, piecing together clues from the faint and fleeting light it reflects. 2 of the most powerful diagnostic tools in their arsenal are color and reflectivity. Every subtle shade of an object's reflected sunlight, every tiny fluctuation in its brightness provides vital information about its chemical composition, its surface texture, and the alien environment in which it was born. When first observed, 3I Atlas appeared to have a slightly bluish-green hue, a color that is commonly associated with comets that are rich in volatile ices. This suggested the presence of specific molecules like cyanogen and diatomic carbon in its faint coma. These gases are known to glow with a characteristic greenish-blue light when they are excited by the ultraviolet radiation from the sun. The presence of these molecules is a strong indicator that 3Y Atlas is an icy, volatile-rich object more akin to a comet than a rocky asteroid like Oumuamua. It tells us that it was born in the cold, distant regions of a star system, a place where these ices could survive for billions of years. Its albedo, or surface reflectivity, offered another crucial piece of the puzzle. By measuring how much sunlight it reflected, astronomers determined that its surface is incredibly dark, reflecting only about 4 to 10% of the light that hits it. This makes it nearly as dark as a lump of charcoal. This low albedo is a common feature of the long-period comets in our own solar system, and it hints that the surface of 3I Atlas is covered with a thick layer of complex carbon-rich organic material. This dark reddish crust likely built up over the millions of years it spent drifting through the harsh environment of interstellar space, constantly bombarded by high-energy cosmic rays. This radiation can transform simple bright ices into more complex, darker organic compounds, a process known as space weathering. Yet the brightness of 3I Atlas did not remain constant. Its light curve, a plot of its brightness over time, showed subtle but regular fluctuations. These variations suggest that it has an irregular shape or perhaps a patchy surface, with some areas reflecting more sunlight than others. Some regions may still have relatively fresh, bright ice exposed on the surface, while other parts are covered in the darker, older weathered material. Comparing its color and reflectivity to the other interstellar visitors highlights its unique character. Oumuamua displayed an unusual reddish color, suggesting its surface was extremely weathered, perhaps even metallic. Borisov, in contrast, had a more classic neutral color similar to the comets from our own Oort cloud. 3. I Atlas seems to be closer to Borisov in its icy, volatile, rich composition, but its relatively weak activity and dark surface suggest that it may have a thicker crust of processed material partially insulating the ices that lie beneath. The color and reflectivity of 3I Atlas tell a story of an extraordinary and ancient journey. Over its millions of years of interstellar travel, cosmic rays and micrometeoroid impacts have gradually reshaped its surface, building up a dark organic film, while the pristine ices buried deep within its interior remained largely preserved. The fact that it still showed some active outgassing when warmed by our sun is a sign that much of its interior has remained untouched since the day it was ejected from its home star system. Spectroscopic studies of the sunlight reflected from its coma have confirmed the presence of water ice and carbon monoxide, two of the most common ingredients in the comets of our own solar system. However, the ratio of these compounds may be different, a subtle chemical fingerprint that could reveal whether 3I Atlas formed around a sun-like star or a cooler, smaller red dwarf. An unusually high ratio of carbon monoxide to water, for example, could suggest that it originated in a far colder, more distant region of its planetary system than is typical for our Kuiper Belt objects. The age of its journey can also be inferred from its reflective properties. A very bright icy surface would suggest a recent ejection from its home system. A very dark weathered surface points to a much longer period of interstellar travel. The modest reflectivity and dark crust of 3I Atlas suggest a long voyage, perhaps tens of millions of years, enough time to build up a thick, black organic layer while still preserving its frozen heart. Each of these details, teased from the faint and distant light of this cosmic messenger, adds another piece to the puzzle, helping us to understand the diversity of worlds across our galaxy, and to begin to answer the question of how special or how common our own solar system truly is. Determining the size of an object as distant and faint as 3I Atlas is a significant challenge for astronomers. With no spacecraft to fly by and take a direct photograph, they must rely on indirect methods, primarily by measuring how much sunlight it reflects. This technique, called photometry, allows them to estimate an object's diameter by combining its observed brightness with an educated guess about its surface reflectivity or albedo. The early photometric studies of 3I Atlas indicated that it is small by planetary standards, but still a considerable object. The best estimates place its effective diameter somewhere between 60 and 120 meters. The range of this estimate reflects the uncertainty in its albedo. If its surface is dark and dusty, covered in carbon-rich material, like many long-period comets, it would need to be closer to the larger end of that range to account for its observed brightness. If, on the other hand, it has significant patches of bright, reflective, fresh ice on its surface, it could be smaller, closer to the lower end of the range. For context, Oumuamua was estimated to be roughly 100 meters long, though its highly elongated cigar-like shape made precise measurements difficult. Comet Borisov, in contrast, was a true giant with a nucleus possibly more than a kilometer in diameter. 3I Atlas sits neatly between these two extremes, closer in scale to Oumuamua, but with a more comet-like appearance. Its size is also similar to that of many of the smaller comets in our own solar system, suggesting that the processes that create and eject these icy bodies may produce objects of a similar scale across different star systems. The brightness of 3I Atlas was observed to vary as it rotated, a clear sign that it is not a perfect sphere. It is likely elongated or irregular in shape, perhaps a jagged shard of rock and ice that was violently torn away from a larger body in its home system. This irregular shape makes pinning down its exact size even more difficult, as the amount of light it reflects changes depending on its orientation relative to us. The very rarity of spotting these interstellar travelers is partly a consequence of their small size. Even at its brightest, 3I Atlas was a faint object visible for only a brief period and only with moderate to large telescopes. Had it been even half its estimated size, it likely would have passed through our solar system completely unnoticed. Its modest size also has implications for its structural integrity. Smaller bodies are more vulnerable to being torn apart by the gravitational and thermal stresses they experience when they pass close to a star. And yet 3I Atlas appeared to be sturdy enough to survive its journey through our inner solar system. While it showed some faint signs of outgassing, this was a typical gentle comet-like behavior, not a sign of catastrophic disintegration. The scale of 3I Atlas also helps us to understand the likely population of these interstellar objects. If it is representative of a larger population of interstellar comets, then the Milky Way galaxy may be filled with countless similar icy fragments. Based on the statistical estimates drawn from the 3 confirmed discoveries so far, there could be billions of these icy wanderers drifting between the stars, most of them ejected during the chaotic early phases of planet formation. Future sky surveys will likely uncover many more, helping astronomers to build a clearer picture of the size distribution of these tiny travelers, even as the vast majority of them remain too faint and too small to ever be detected. However, the small size of 3I Atlas raises intriguing questions about its origin. Is it a pristine primordial comet, a small independent body that was ejected intact from its home system? Or is it a fragment of a much larger body, a piece of a shattered exoplanet, or a disrupted dwarf planet? Its irregular shape and unusual light curve may suggest the latter, that it is a piece of a larger, more complex world, a cosmic shard that carries the story of a violent and cataclysmic past. Its tiny scale, combined with its long and lonely journey, offers a window into the hidden and dynamic world of interstellar debris, bridging the gap between the study of planet formation and the grand exploration of our galaxy. When astronomers study a newly discovered object like 3I Atlas, one of the first and most fundamental questions they ask is whether it behaves more like a comet or an asteroid. This is not just a matter of classification. It is a question that goes to the very heart of what the object is made of and the story of its long journey. Comets are the active dynamic bodies of the solar system. When warmed by the sun, their icy surfaces release gas and dust in a process called sublimation, creating a glowing cloud or coma, and often a long sweeping tail. Asteroids, in contrast, are typically quiet and inert, dry, rocky bodies that simply reflect sunlight without any significant outgassing. 3I Atlas does not fit neatly into either of these categories. It seems to occupy a fascinating middle ground, blurring the line between comet and asteroid and raising new questions about how interstellar objects are shaped by their long and lonely voyages between the stars. When it was first spotted, 3I Atlas showed faint but definite hints of activity. Careful photometric measurements revealed a thin, hazy halo of dust and gas around its core, a sign that some of its frozen ices were indeed sublimating as it drew near the sun. However, this coma was incredibly weak. It was more active than the mysterious and silent Oumuamua, which had no visible coma at all. But it was far, far weaker than the dazzling display of Comet Borisov, which produced a classic bright cometary tail. 3I Atlas therefore sits in a gray area, active enough to show that it carries volatile ices, but quiet enough to suggest that much of its surface is sealed under a hardened or insulating crust. This faint, subdued activity tells a story. One possibility is that 3Y Atlas has been drifting through interstellar space for millions of years. Over that vast timescale, the constant bombardment of cosmic rays and micrometeoroids may have baked and processed its surface, creating a hard, organic-rich crust. This shell could act as an insulating layer, trapping the more volatile ices deep within its interior and preventing them from escaping easily, even when warmed by the sun. Another possibility is that 3Y Atlas was never very rich in these volatile ices to begin with. Perhaps it formed in a warmer region of its home star system than is typical for comets, resulting in a body that was more rocky and less icy from the start. A comparison of its dust production rate with other comets is telling. Borisov at its peak was spewing out hundreds of kilograms of dust every second, creating a spectacular sight. In contrast, 3I Atlas, even at its most active, was releasing only a few kilograms of dust per second. This weak outflow explains why it never developed a grand sweeping tail. Yet even this faint trickle of gas and dust was scientifically priceless. By studying the light coming from its thin coma, astronomers were able to identify traces of water vapor and carbon monoxide. These are exactly the kinds of ices that are expected to form in the cold outer regions of planetary systems. The particularly strong signal of carbon monoxide was especially intriguing, as it suggests that 3Y Atlas was born in an extremely frigid environment, perhaps even colder and more distant from its parent star than our own Kuiper belt. This fits perfectly with the idea that such objects are ejected from the icy frontiers of young, unstable planetary systems. The lack of a grand tail also gives us clues about its internal structure. It seems likely that the heat from the sun was only able to penetrate to a shallow depth, causing gases to seep out slowly and gently rather than erupting explosively. Its surface, reshaped over eons by radiation and countless tiny impacts, may have developed a hardened, porous shell that protected the deeper layers of ice from being released all at once. This raises a larger and more profound question: do all interstellar objects evolve in the same way Borisov remained isoric and spectacularly active? Oumuamua was silent and apparently bone-dry, and 3I Atlas lies somewhere in between. Perhaps some of these interstellar wanderers develop thick, insulating crusts that effectively shut down their cometary activity, while others, perhaps younger or on a different kind of journey, remain relatively pristine and untouched. These differences are not just curiosities. They are helping astronomers to understand the complex and long-term effects of the harsh interstellar environment on small icy bodies. There is also a deeper implication. The faint coma of 3I Atlas connects to the fascinating idea of panspermia, the theory that the seeds of life in the form of complex organic molecules could travel between the stars aboard comets. If an object can still carry and release organic-rich material after such an unimaginably long journey, then it could act as a natural courier, delivering the building blocks of life to new worlds. By comparing Oumuamua, Borisov, and now 3I Atlas, astronomers are beginning to build their first small sample of these visitors from other worlds. And what that sample is telling us is that the population of these interstellar travelers is astonishingly diverse, each one with its own unique story, a story that is written in its chemistry, its shape, its motion, and its quiet or spectacular dance with the light of a star. When astronomers discovered the first few interstellar visitors, it was as if they had opened a door to a new and unknown room in the cosmic mansion. And each time a new visitor has arrived, it has shown them something different, something unexpected. The first Oumuamua was a profound mystery, a silent, elongated object that defied easy classification. It showed none of the typical signs of a comet, yet its strange non-gravitational acceleration hinted at some unseen force, perhaps outgassing, that was invisible to our telescopes. In stark contrast, the second visitor, Borisov, was comfortingly familiar. It behaved exactly like a classic long-period comet from our own solar system, with a bright coma and a long, sweeping tail. And now, standing between these two extremes, is 3I Atlas. It is icy like a comet, but its activity is strangely muted, as if its surface has been sealed by a long and arduous journey. This middle ground behavior is strengthening an exciting idea. Interstellar objects are not all the same. They represent a wide and diverse population of cosmic travelers, each one shaped by its unique birthplace and its long, lonely history. One of the most important clues to an object's history is its rotation. Whether it spins smoothly on a stable axis or tumbles chaotically through space can reveal a great deal about its internal structure, its surface properties, and the forces it has encountered on its journey. To measure an object's rotation, scientists create a light curve, a graph of its brightness over time. As an irregularly shaped object spins, it reflects different amounts of sunlight, causing its brightness to flicker in a regular repeating pattern. The light curve of 3I Atlas revealed that it is indeed rotating, completing one turn in about 9 to 12 hours. This is a moderate spin rate, not unusual for a comet-sized body. It tells us that 3I Atlas is structurally sound enough to have survived its long journey without being spun apart. But the light curve also revealed something more intriguing. The pattern of its flickering was not a simple smooth wave. It had uneven peaks and dips, a sign that the object is not a simple uniform ellipsoid, but has a more complex, irregular shape. It might also mean that 3Y Atlas is not spinning cleanly around a single stable axis, but is in a state of complex rotation or tumbling. Tumbling is not unusual for small bodies in the solar system. It can be caused by collisions or close gravitational encounters that disrupt a smooth spin. For an interstellar traveler, this makes perfect sense. As 3I Atlas roamed the galaxy for millions of years, it would have been subject to gentle gravitational tugs from passing stars and countless tiny impacts from micrometeoroids. Over time, these small but persistent nudges could have easily sent it into a wobbling, irregular tumble. This complex rotation could also help to explain its patchy, uneven cometary activity. As it tumbles, different parts of its surface would be exposed to sunlight at unpredictable times, potentially causing sudden localized bursts of outgassing from any exposed patches of fresh ice. If it is indeed tumbling, it also tells us something about its internal strength. A fragile, loosely bound object would likely be torn apart by the stresses of such a complex rotation. The fact that 3Y Atlas has held together suggests that it has a significant amount of internal cohesion, perhaps held together by a tough mixture of ice and compacted dust. Its rotation period also provides clues about its past. Each time an object like this passes close to a star, the outgassing of its ices can create small but persistent jets of force that act like tiny rocket thrusters, gradually altering its spin. The fact that 3I Atlas has a moderate spin rate suggests that it has either experienced very few of these close stellar encounters or that its protective surface crust has kept its outgassing weak and controlled, preventing it from being spun up to dangerous speeds. Another possibility is that its unusual spin dates all the way back to the violent event that ejected it from its home system. A close encounter with a giant planet, the kind of event that could provide the gravitational slingshot needed to achieve escape velocity, could have easily set it tumbling its complex rotation, a fossil record of the very moment its cosmic voyage began. When compared with the other interstellar visitors, 3I Atlas once again seems to be a hybrid. Oumuamua was clearly in a state of complex, chaotic tumbling, and it may have been extremely elongated. Borisov, in contrast, appeared to be rotating in a more ordinary, stable manner, like a typical solar system comet. 3I Atlas combines elements of both its spin, moderate but possibly unstable, reinforcing the idea that these interstellar objects are a diverse population, each with its own unique story, written in the language of its motion. Rotation is only one part of the puzzle. Another powerful tool astronomers use is spectroscopy, the analysis of the light that is reflected from an object's surface and emitted by the gas and dust in its coma. By breaking this light into its constituent colors, its spectrum scientists can identify the unique chemical fingerprints of specific atoms and molecules. For an interstellar traveler, these fingerprints are like a message in a bottle, revealing the chemical composition of a solar system beyond our own. And when astronomers studied the spectrum of 3I Atlas, they found something remarkable. This strange visitor from another star looked surprisingly familiar. It carried many of the same ingredients as the comets we know from our own solar system, a discovery that hints at the tantalizing possibility that the fundamental processes of planet and comet formation may be universal across the galaxy. The clearest chemical signal in the spectrum of 3I Atlas was that of water ice. This was not a surprise, as water is one of the most abundant molecules in the universe. Its presence confirmed that 3Y Atlas was born in a cold, distant region of its home system, far from the warming glow of its parent star. But it was not alone. The comet was also releasing volatile gases like carbon monoxide and carbon dioxide, both of which are also common in the comets of our solar system. However, the exact ratio of these gases can vary depending on where and how a comet forms. And 3I Atlas was found to have a slightly higher concentration of carbon monoxide relative to water than is typical for the comets we know from our own Kuiper belt. This suggested something fascinating. Perhaps it formed in an even colder, more distant region of its system than our local comets usually do. Or perhaps its parent star was dimmer and cooler than our Sun, pushing the ice-forming zone farther out. Spectroscopy also hinted at the presence of more complex chemicals, possibly organic molecules. These showed up as faint absorption features in the ultraviolet and near-infrared light. Such compounds are thought to form when cosmic rays batter the icy surfaces of these objects during their long, lonely journeys through interstellar space, a process that is known to create a dark, reddish, organic-rich crust. The detection of this organic material is especially exciting as it strengthens the idea that the raw ingredients for life might be spread across the galaxy by these wandering objects. The data also gave astronomers a sense of how ancient and untouched its material might be. While Borisov appeared to be chemically pristine, almost a perfect analog for a solar system comet. 3I Atlas seemed to have a more complex history. Its surface looked processed and weathered by its long exposure to radiation, while its deeper interior still contained fresh, unaltered ice. This layered structure, an old weathered crust hiding younger, purer ice beneath, is exactly what scientists expect to see in a true long-duration interstellar traveler. Further evidence came from the detection of silicate dust in its coma rocky materials that typically condense in the warmer regions closer to a star. Their presence meant that 3I Atlas was not a pure ice ball, but a composite object, a mixture of both rock and ice. This supports the theory that many of these interstellar objects are ejected during the chaotic early phases of planet formation, when the rocky and icy regions of a young system are violently mixed. Perhaps the most unexpected and profound discovery was also the most ordinary one. Aside from a few subtle differences in gas ratios and the effects of space weathering, 3I Atlas contained no mysterious or exotic ingredients. It was in many ways almost boringly familiar. But that very ordinariness carried with it a powerful and hopeful message. It meant that the same fundamental chemistry that shapes comets in our corner of the galaxy is likely happening in star systems everywhere. The raw materials for planets, for oceans, and perhaps even for life itself are not rare and special. They are widespread, universal, scattered across the Milky Way, waiting to be gathered and shaped by countless other worlds. If comets that wander into our solar system from other stars look and act so much like the comets that belong to our own solar family, then what truly sets them apart? The discovery of 3I Atlas as only the third confirmed interstellar object has given astronomers a new and crucial point of comparison in their quest to understand the incredible variety of these galactic wanderers. Each of these visitors carries with it a unique biography, a story that is written in its chemistry, its shape, its motion, and its level of activity. And by carefully comparing how 3I Atlas differs from the two that came before, 1I Oumuamua and 2I Borisov scientists are beginning to build their first tentative picture of the kinds of raw materials that other planetary systems produce and how those materials are altered by their long and lonely exiles in the interstellar dark. The most striking differences between these three travelers lie in their appearance and their level of cometary activity. Borisov was unmistakably a comet. It was active and vibrant, sprouting a brilliant glowing coma and a long sweeping tail of gas and dust as it was warmed by our sun. It was in almost every respect a textbook example of a long-period comet, its only distinguishing feature being its hyperbolic interstellar orbit. Its chemistry confirmed this familiar story. It was made of the same kinds of frozen ices in roughly the same proportions as the comets from our own solar system. Oumuamua, however, could not have been more different. It was a silent enigma. It showed no coma, no tail, no sparkling jets of gas. It looked more like a dry, inert asteroid, or perhaps a heavily weathered rock whose surface had been sealed by a hardened insulating crust that trapped any remaining ices deep within. 3. I-Atlas lies in a fascinating space between these two extremes. It did show a faint whisper of cometary activity, a ghostly halo of dust and gas that revealed the presence of surviving ice. But its activity was incredibly weak, a mere trickle compared to Borisov's dramatic outgassing. Much of its surface, like Oumuamua's, seemed to have been locked away beneath a hardened shell, a crust that was forged during its long exposure to the harsh radiation of interstellar space. And yet it was not completely lifeless. Sensitive instruments could still detect the faint spectral signatures of water vapor and carbon monoxide seeping from within, a sign that pristine, untouched ices remained in its core, waiting for a moment of warmth to be released. The chemistry of these bodies adds another layer to their divergent stories. Borisov's composition was strikingly familiar. Oumuamua's silence made its chemistry difficult to study directly, but its unusual reddish color suggested that its surface was coated with complex organic molecules that had been baked and transformed by millions of years of cosmic ray bombardment. 3I Atlas once again seems to be a blend of both. Its reflected light revealed a mixture of water-ice carbon monoxide and perhaps complex hydrocarbons, hinting that it was born in the frozen outskirts of a planetary system, but had been significantly altered by its long journey. The shapes and spins of these objects tell still more of their individual tales. Oumuamua was by far the strangest, with its highly elongated cigar-like or perhaps flat pancake-like shape and its chaotic tumbling rotation. Its bizarre behavior sparked a flurry of speculative theories, from the idea that it was a fragment of a tidally shattered planetesimal to the more exotic possibility that it was an alien artifact. Borisov, in contrast, was completely ordinary. It had a roughly spherical nucleus and rotated in a stable, predictable manner, just as we would expect from a typical solar system comet. And 3I Atlas once again rests in the middle. Its brightness pattern suggests that it is somewhat elongated and may even be in a state of complex tumbling rotation, though not as dramatically as Oumuamua. This hints that while it was jostled and disrupted during its violent ejection from its home system, it managed to hold together as a single cohesive body. Their sizes also highlight their diversity. Borisov was the giant among them, with a nucleus more than a kilometer in diameter. Oumuamua was tiny, barely 100 meters long, a cosmic needle in a galactic haystack. And 3I Atlas was even smaller, measuring somewhere between 60 and 120 meters across. Its modest size explains why it was so difficult to detect and why it remained visible for only a very brief window of time. Why do they behave so differently? The variations in their activity may reveal not just what they are made of, but also how long they have been wandering the interstellar dark. Borisov's fresh ichorish nature might suggest that it was ejected from its home system relatively recently, before cosmic radiation had time to process its surface. Oumuamua's silence, on the other hand, hints that it had been drifting for eons, long enough to build up a thick, radiation-hardened crust that effectively sealed away its inner ice. And 3I Atlas, with its faint but still detectable activity, seems to be in between weathered and ancient, but not yet entirely dormant. Even their birthplaces may have left their mark. Borisov almost certainly formed in a system very much like our own. Oumuamua's exact origin is still a mystery, but its dry, processed surface suggests that it might have once been part of a larger, differentiated body, or perhaps formed in a warmer inner region of its system. And 3I Atlas, with its unusually high concentration of carbon monoxide, points to a birthplace in an even colder environment, perhaps in the distant frigid outskirts of a dim red dwarf star system. Each of these visitors is a unique individual, a single data point in a new and exciting field of astronomy. And together, they are beginning to paint a picture of the galaxy as a place of incredible diversity. A cosmos filled with a rich and varied population of wandering worlds, each with its own story to tell. One of the most exciting and speculative ideas about the mysterious traveler 3I Atlas is that it might not be a primordial comet at all, but something far more dramatic, a broken-off piece of a much larger world. Imagine a shard of ice and rock once part of a developing planet, or a young moon being violently ripped away from its birthplace in a cosmic cataclysm and hurled into the endless void between the stars. This idea, while bold, is supported by several subtle clues in the data we have gathered. If true, it would mean that 3I Atlas is not just a cosmic curiosity, but a priceless sample of raw planetary material from deep inside another solar system, a fossil of an ancient shattered world. The idea that interstellar space might be filled with such fragments is not as far-fetched as it sounds. The birth of planets is a violent and chaotic process. In the early turbulent youth of a star system, newly formed planets, moons, and smaller bodies called planetesimals are constantly jostling for position, their orbits crossing and their gravitational fields interacting. This can lead to catastrophic collisions that can smash entire worlds into pieces, scattering them like cosmic shrapnel. The immense gravity of giant planets like Jupiter in our own solar system adds to the chaos, acting as a powerful slingshot that can eject smaller bodies from the system entirely. Computer simulations of planet formation suggest that for every stable planet that forms, countless smaller bodies are cast out, lost to the interstellar void. Over billions of years, this process could fill our galaxy with trillions of these wandering fragments of shattered planets and moons. Several features of 3I Atlas strengthen the idea that it might be one of these cosmic refugees. First, its irregular, elongated shape, inferred from the way its brightness flickers as it rotates, is more consistent with a piece of broken debris than a smooth, compact cometary nucleus. Second, its chemical makeup is unusual, while it contains the ices that are typical of a comet. Spectroscopic studies also show the presence of silicate dust, rocky materials. This suggests that it might be a fragment of a differentiated body, a larger world that had already separated into layers with a rocky core or mantle and an icy crust. If such a body were to be destroyed in a collision, a fragment like 3I Atlas could contain a mixture of both of these materials. This would also help to explain its weak, subdued cometary activity. While a pristine comet like Borisov was rich in easily accessible surface ice, the activity of 3I Atlas was far fainter. Its outer layers may be more rocky or have been processed and hardened by its long journey, hiding the more volatile ices deep within its interior. This would allow only a small amount of gas and dust to escape when warmed by the sun. Its dark surface, coated with complex carbon-rich organic material, adds to the mystery. While any interstellar object will be weathered by cosmic radiation over millions of years, a planetary fragment would have started with a more complex and varied mixture of rocks, ices, and minerals than a simple primordial comet. Over time, radiation would transform these materials, leaving behind the blackened, processed crust we see today. When compared to Oumuamua, the first known interstellar visitor, the similarities are intriguing. Oumuamua was also highly elongated, inactive, and puzzling, leading some scientists to suggest that it too could be a fragment of a larger body that was torn apart by the tidal forces of its parent star. 3I Atlas, though slightly more comet-like than Oumuamua, still seems to occupy a space somewhere between Oumuamua's fractured stillness and Borisov's bright, icy vitality. If 3I Atlas is indeed a planetary fragment, then the event that ejected it must have been far more violent than the gentle gravitational nudges that typically send comets from the Oort cloud on their long journeys. It would require a true cataclysm, a giant planet migrating through its system and scattering the inner rocky worlds, or even a close flyby of another star that destabilizes the orbits of an entire planetary family. Such events, far from being rare, are now thought to be common in the early chaotic lives of many star systems. The stakes of this theory are enormous. If 3I Atlas is a planetary fragment, then these interstellar objects are not just cosmic curiosities. They are free samples of alien worlds, pieces of planets and moons that have been flung across the galaxy and delivered to our cosmic doorstep. By analyzing their chemistry, we could gain precious insights into the composition of the inner layers of planets that orbit other stars, knowledge that we could never obtain by simply observing their distant surfaces. This possibility also touches on an even deeper question: the spread of life itself. Could such planetary fragments act as protected vessels carrying the seeds of life between star systems? While the odds of life surviving such a journey are incredibly small, a large rocky fragment could provide significant shielding from the harsh radiation of interstellar space, protecting any delicate organic molecules or even dormant microbes that might be trapped within its interior. Of course, proving that 3I Atlas is a planetary fragment will not be easy. Almost everything we know about it comes from the faint and fleeting light it reflected during its brief passage. For now, it remains an open and exciting debate, one that may only be settled by the discovery of more of these interstellar visitors. As we build a larger sample of these cosmic travelers, we may begin to see patterns emerge, with some behaving like traditional comets and others like Oumuamua and perhaps 3I Atlas, showing the telltale signs of being the fractured wandering orphans of long-dead worlds. And this raises one final tantalizing question: if the galaxy is truly filled with such fragments, why do we see so few of them? The answer, it seems, has more to do with the limits of our own vision than with the emptiness of the cosmos. It may seem surprising that in all of human history we have only confirmed the existence of 3 visitors from other star systems. If planets and stars across the galaxy are constantly flinging comets, asteroids, and fragments of rock into space, shouldn't our skies be filled with these cosmic wanderers? The truth is that interstellar objects are likely incredibly common, but they are also fiendishly difficult to spot. Their apparent rarity in our catalogs has more to do with the profound challenges of detecting them than with their actual numbers in the galaxy. Several daunting obstacles stand in our way. The first is a simple matter of size and brightness. Interstellar objects are typically quite small, often no more than a few hundred meters across. Compared to even a small dwarf planet, they are minuscule. This small size means they reflect very little sunlight. And to make matters worse, their surfaces have usually been darkened and weathered by their long exposure to the harsh radiation of interstellar space. Many, like 3I Atlas, have an albedo that is as low as that of charcoal, making them almost perfectly black. Unless they happen to pass very close to the Earth, or unless they are active comets that develop a bright glowing tail, they remain all but invisible tiny dark needles in a vast glittering galactic haystack. The second great difficulty is their speed. Interstellar objects move far faster than most of the comets and asteroids that are native to our solar system. They race through space at tens of kilometers per second, darting across the inner solar system in just a few short months. This means that by the time they are close enough and bright enough to be detected, they are often already on their way back out into the darkness, giving astronomers only a fleeting, precious window of time to study them. Oumuamua itself was only discovered after it had already swept past the Sun, leaving scientists with just a few precious weeks to observe it before it disappeared forever. The third obstacle has been the nature of our astronomical surveys. For a long time, we simply were not looking in the right way. Traditional astronomical surveys were often designed to study bright, slow-moving objects like stars and galaxies, not faint, fast-moving specks. Even the surveys that are dedicated to finding near-Earth asteroids like the Atlas project can only scan certain parts of the sky each night, leaving huge regions unobserved. Spotting a tiny, dim, fast-moving interstellar object against a backdrop of billions of stars has been like trying to notice a single dark bird flying at night. Another challenge is that these wanderers are only at their brightest for the short period when they are close to the Sun. Far out in the cold depths of space, they are far too faint to detect. Many may remain perpetually dim. Oumuamua, for example, never developed a cometary tail, and so it remained faint even at its closest approach. This means that countless such visitors may have already slipped through our solar system completely unseen. And yet our best population models suggest that interstellar objects are astonishingly abundant. Some astronomers estimate that for every single star in the Milky Way galaxy, there may be trillions of these icy and rocky fragments drifting through the interstellar void. Most of them were likely ejected billions of years ago during the violent and chaotic early days of planet formation. Our own solar system probably contributed to this galactic diaspora, ejecting countless comets and asteroids when Jupiter and Saturn migrated to their current orbits. Other star systems almost certainly did the same, gradually filling the galaxy with a vast, unseen population of wandering debris. The cosmos may be swarming with these lonely travelers. We just cannot see most of them. Even so, our capabilities are rapidly improving. In just a few short years, astronomers have gone from knowing of 0 of these objects to discovering 3. This remarkable leap forward is a direct result of the new generation of powerful automated sky surveys like Pan-STARRS and Atlas, which sweep the heavens every night, their software tirelessly searching for anything that moves in an unusual way. And the future looks even brighter. The upcoming Legacy Survey of Space and Time, to be conducted at the Vera C. Rubin Observatory, is expected to revolutionize this hunt. With its massive mirror and its lightning-fast wide-field camera, it may discover not just 1 or 2, but dozens or even hundreds of interstellar objects every single decade. But even with this new technology, the majority of these travelers will still escape our notice. Many will pass far from the Earth, too distant for even our most sensitive telescopes to catch. The majority are probably only a few tens of meters across, far smaller than 3.1 Atlas. These miniature wanderers will glide silently through our solar system, their passage unrecorded, their secrets intact. Still, we can learn a great deal from the few that we do catch. The light curve of 3.1 Atlas. The record of its changing brightness tells us that it is not a simple sphere. Its brightness rises and falls in a steady rhythm every 9 to 12 hours, matching its rotation. But the variations are modest, indicating that it is not as extremely elongated as Oumuamua, whose brightness swung dramatically by a factor of 10 due to its bizarre cigar-like shape. Even so, the uneven peaks and dips in 3.1 Atlas's light curve suggest a lumpy, irregular surface, perhaps scarred with ridges, craters, and fractures, a cosmic shard that still carries the marks of its long and violent history. An irregular shape is exactly what we would expect from an object that is a fragment of a larger shattered world. Unlike large planets and moons, which are pulled into nearly perfect spheres by their own gravity, smaller bodies retain their odd, lumpy outlines. The irregular brightness of 3.1 Atlas suggests not only an uneven shape, but also a patchy surface with some areas darkened by ancient radiation and others still glittering with patches of fresh reflective ice. Interestingly, the variation in its brightness is not extreme. This might mean that over its millions of years of interstellar travel, 3.1 Atlas has been slowly smoothed and eroded by a constant rain of micrometeoroids and the gentle sublimation of its surface ice, a kind of cosmic sandpaper that has softened its most jagged edges. And yet it is still far from smooth, a small ancient traveler from another star, scarred but enduring. When astronomers compare its shape and rotation to the other two interstellar visitors, the differences are striking and informative. Oumuamua had a very strange, highly elongated form and was tumbling chaotically, leading to wild speculation about its origin. Borisov, in contrast, appeared to be a textbook comet with a roughly spherical nucleus and a stable rotation. And 3I Atlas rests somewhere in between, less like a pristine cometary nucleus and more like a shard of ice and rock that was torn from a larger frozen body. It is irregular, but not in a way that is alien or unexplainable. This shape also determines how the object reacts to sunlight. A lopsided body heats unevenly. Some patches of its surface may remain dormant, while others, where fresh ice is exposed, can suddenly erupt with jets of gas. These jets can act like miniature rocket engines, applying a gentle but persistent torque that can alter the object's spin over time. The faint irregularities seen in 3Y Atlas's light curve may be a sign of this quiet tug-of-war between heat ice and gas. But there is another question. Does its uneven shape make it fragile? Compared to a solid spherical body, a jagged shard often lacks structural strength. And yet its very survival during its passage through our solar system shows that despite its irregularity, it is still tough enough, cohesive enough to endure the moderate thermal and gravitational stresses of a close encounter with a star. Even so much remains uncertain. Because 3I Atlas is so faint, the fine details of its outline remain hidden. But in the future, with the advent of more powerful telescopes, we may one day be able to resolve the shapes of these wandering fragments with far greater precision, and in those shapes we may be able to read the deeper stories of their violent births and their long and lonely journeys between the stars. Finding the exact birthplace of 3I Atlas is one of the greatest challenges in modern astronomy. A cosmic detective story that spans millions of years and vast tracts of the Milky Way. Once an object is ejected from its home star system, it begins a long and lonely journey, its path constantly being nudged and deflected by the gravitational influence of the entire galaxy. Tracing this path backward in time is a task of immense complexity, fraught with uncertainty. And yet astronomers persevere, using every clue at their disposal to narrow down the regions of space from which this mysterious traveler might have come. By carefully retracing the object's hyperbolic orbit, they can determine the direction from which it approached our solar system. For 3I Atlas, this path seems to point roughly toward the constellations Carina and Scorpius, two brilliant regions of the southern sky that are rich with stellar nurseries, vast, turbulent clouds of gas and dust where new stars and planets are being born. These are natural candidates for its birthplace, as the chaotic, crowded environments of young star clusters are thought to be the most common source of ejected interstellar objects. One strong possibility is that 3Y Atlas was born in a system much like our own, orbiting a young sun-like star that was surrounded by massive gas giant planets. In such systems, the giant planets often migrate through the early protoplanetary disk, their immense gravity scattering smaller icy and rocky bodies in every direction. Some of these unfortunate wanderers are sent crashing into their parent star, while others are flung into the cold darkness of interstellar space, destined to roam the galaxy as cosmic exiles. The fact that 3Y Atlas is a composite object containing both water ice and silicate rock supports this idea. As such, mixing is common in the turbulent zones where planets form. But there is another compelling candidate, a red dwarf star system. Red dwarfs are the most common type of star in the Milky Way, and many of them are thought to host planetary systems. Because red dwarfs are smaller and cooler than our Sun, their habitable zones and their ice-forming regions lie much closer to the star. This makes any planets or planetesimals in such systems more susceptible to being ejected by gravitational interactions or the close passage of another star. The unusually high amount of carbon monoxide detected in the coma of 3Y Atlas may hint at an origin in such a colder environment, as carbon monoxide ice can condense at lower temperatures than water ice. Even so, tracing it back to a single specific star is currently impossible. The Milky Way is a dynamic, swirling city of stars, and its inhabitants are constantly moving. By the time 3I Atlas arrived at our cosmic doorstep, its parent star had likely drifted far from its original position. Even with the incredibly precise measurements of stellar positions and motions from missions like the European Space Agency's Gaia spacecraft, the uncertainties in reconstructing a path over tens of millions of years are simply too large. So far, no single star has been identified as the definitive birthplace of this wandering visitor. The way in which it was ejected also provides clues. Most interstellar objects are thought to be cast out during the earliest, most chaotic stages of planet formation, typically within the first 100 million years of a system's life. If 3Y Atlas was born inside a crowded young star cluster, where neighboring stars often pass close to one another, the chances of it being ejected would have been even higher. In such dense stellar environments, a close flyby of another star can easily destabilize an entire planetary system, launching comets and planetary fragments into the galaxy at high speed. If this was the case, 3I Atlas may have been expelled very early in its system's history and has spent tens of millions of years drifting alone through the Milky Way. Its surface tells a similar story. The dark carbon-rich crust that seems to cover 3I Atlas is a sign of a long and arduous journey. Constant exposure to cosmic rays slowly alters the chemistry of an object's surface, building up a dark weathered layer. This suggests that 3Y Atlas was ejected long ago, a true ancient mariner of the interstellar seas. But this weathered crust may also be a protective shield, preserving the pristine, untouched ices of its interior. And in those ices may lie the answer to an even deeper question. Did this messenger from another world carry with it the very building blocks of life? The possibility that an interstellar traveler like 3I Atlas could be a carrier of organic molecules. The basic chemical ingredients for life is one of the most exciting and profound ideas in modern astrobiology. If true, it would mean that this frozen wanderer is not just a geological curiosity, but a potential messenger, a cosmic courier carrying the seeds of life's potential across the vast distances between the stars. Organic molecules are carbon-based compounds, the fundamental building blocks of more complex substances like amino acids and proteins, which are essential for all known life. The idea that these molecules could travel between star systems, a concept known as panspermia, suggests that the raw materials for life might not need to arise independently on every habitable world, but could be delivered from a common galactic stock. The careful study of the light reflected from 3I Atlas strongly suggests that it does indeed contain organic compounds. The faint greenish glow observed in its coma is a characteristic signature of cyanogen and diatomic carbon molecules that are typically formed from the breakdown of larger, more complex carbon-rich molecules by sunlight. This means that the nucleus of 3I Atlas is likely coated in a layer of this complex organic matter. Similar organic materials have been discovered on the comets within our own solar system, and they are widely believed to be the chemical precursors to life. This makes the discovery of them on an interstellar object incredibly important, as it shows that the same prebiotic chemistry that may have seeded life on Earth could be a common process in planetary systems all across the galaxy. The surface of 3I Atlas is also unusually dark, another sign of the presence of complex organics. Its low albedo is typical of comets that are coated in a substance called tholins, reddish-brown organic solids that are formed when ultraviolet radiation and cosmic rays strike simple ices like methane and nitrogen over millions of years. During its long drift through interstellar space, 3I Atlas would have been constantly bombarded by this high-energy radiation, slowly building up a thick crust of these tholins. This outer layer acts as both a diary recording the long chemical history of the object's journey and a shield protecting the more volatile ices of its interior from being destroyed. These findings are remarkable because they demonstrate that this kind of organic chemistry is not unique to our solar system. The fact that 3I Atlas born around another star has developed the same kinds of carbon compounds as our own comets suggests that prebiotic chemistry may be a normal and widespread feature of the Milky Way. In young star systems, these organic coated ice grains are thought to form in the cold outer regions of the protoplanetary disk, the nursery where planets are born. These grains eventually clump together to form comets and planetesimals. Later, if these bodies are delivered to the surfaces of young rocky planets, they can provide a rich source of both water and the organic materials needed to kickstart life. The interior of 3Y Atlas is thought to be even more pristine than its weathered surface. Scientists believe that its radiation-hardened crust may only be a few meters thick. This relatively thin shell could have shielded the inner ices for billions of years, preserving them in the state they were in when 3I Atlas first formed. Deep within its core, there may still be fragile molecules like methanol, formaldehyde, and simple amino acid precursors. If humanity could one day sample this material, we might be able to read a frozen snapshot of the chemistry that existed in another star system long before our own Earth was born. This leads to a profound and almost poetic thought. Objects like 3I Atlas are not just visitors, they are messengers from other suns. As they pass through star systems, they can shed some of their ice and dust, scattering these fine, organic-rich particles into space. These particles might then drift for millions of years before being incorporated into a new generation of stars and planets. In this way, the galaxy is constantly exchanging the building blocks of life between its stars. This would dramatically increase the chances that life could arise wherever the right conditions like liquid water and a stable energy source are present. Even the very existence of 3Y Atlas proves something profound. Planetary systems are not closed boxes. They regularly eject comets, asteroids, and planetary fragments into the interstellar medium. The galaxy may be filled with billions of these objects. If even a small fraction of them carry organics, then the Milky Way is in a constant state of chemical exchange, a vast and interconnected ecosystem where the raw materials for life are continuously being created, transported, and delivered to new worlds. Which planets gave 3Y Atlas the final gravitational push that sent it on its way to us? The answer, it seems, lies in the subtle and powerful dance of the giant planets in our own solar system. The journey of 3I Atlas through our solar system was a delicate and complex dance with gravity. Like a small boat navigating a sea of powerful currents, its path was subtly nudged and deflected by the invisible pull of the planets. The most powerful of these gravitational hands belong to the gas giants Jupiter and Saturn, whose immense masses dominate the outer solar system. When 3I Atlas first swept into our cosmic neighborhood, its path was already set on a hyperbolic trajectory, a one-way ticket that ensured it was just passing through. But this path was not immutable. The gravity of the great planets can act as a cosmic steering wheel, giving a passing object a small push or pull that can alter its speed and direction. By carefully studying these subtle adjustments, scientists can learn a great deal about both the object itself and the powerful forces that shape our solar system. Jupiter, the undisputed king of the planets, is famous for its powerful gravitational slingshot effect. With a mass more than twice that of all the other planets combined, Jupiter's gravity can dramatically reshape the orbits of comets and asteroids, sometimes flinging them out of the solar system entirely, and other times sending them plunging toward the Sun. For 3I Atlas. However, the encounter was not so dramatic. Its closest approach to the Sun was well inside the orbit of Jupiter, so the giant planet's influence was more of a gentle long-distance nudge than a powerful close-range shove. It may have slightly tilted the object's trajectory or given it a tiny boost in speed, but nothing compared to the profound changes Jupiter can inflict on objects that pass closer to it. Saturn, the second largest planet, may have played a more noticeable though still subtle role. The path of 3I Atlas brought it relatively nearer to Saturn than to Jupiter. And while the distance was still vast, Saturn's considerable mass allowed its gravity to reach out and tug on the interstellar visitor. Much like Jupiter, Saturn could not hope to capture the fast-moving object, but it may have added its own small adjustment to its already complex trajectory. The faint but measurable changes in the object's speed and angle as it passed through the outer solar system are a testament to the long reach of these gas giants. And yet when astronomers compared their precise observations with their orbital calculations, they were struck by how steady the motion of 3Y Atlas remained. Despite the immense gravitational pull of both Jupiter and Saturn, its fundamental hyperbolic orbit was barely altered. This was the final definitive proof that it was never a member of our solar family. It was a true interstellar traveler, its own master, its path only slightly perturbed by the planets of our solar system as it passed by them, like a high-speed train passing distant stations. This story of near encounters with the giant planets also raises a fascinating question: how many other interstellar wanderers might have passed through our solar system completely unseen? 3Y. Atlas was small and faint, and was only discovered thanks to the tireless automated eyes of the Atlas survey. If such objects are as common as many scientists now suspect, then dozens, perhaps even hundreds of similar interstellar fragments could be racing through the outer solar system. At this very moment, their paths gently being shaped by Jupiter and Saturn, but their existence completely unknown to us. Their passage a silent and unrecorded event in the long history of our cosmic home. When astronomers announced the discovery of a new interstellar visitor, 3I Atlas, moving at incredible speeds, a natural and immediate question arose in the public mind. Could this strange traveler from the stars pose a danger to Earth? The answer, fortunately, is a clear and unequivocal no. 3. Atlas is rushing through space on a trajectory that never brought it anywhere near our planet. Like the other confirmed interstellar wanderers, its path ensures that it is a harmless, though fascinating visitor. The reason for this is its hyperbolic trajectory. This open, unbound flight path means that it is not trapped by the sun's gravity in a repeating orbit, but is simply passing through the solar system once before it escapes forever back into the interstellar void. Even at its closest approach to the sun, its perihelion, the object remained far from the inner solar system where Earth orbits. Its nearest distance to the Sun was about 0.3 astronomical units, roughly 45 million kilometers. This is about the same distance as the orbit of Mercury. Earth, by comparison, is one full astronomical unit from the Sun, more than 3 times farther out. This means that 3Y Atlas remains safely in the inner sanctum of the solar system, never crossing Earth's path and never posing a threat to any planet. Even if its course had been slightly different, its breathtaking speed would have been a form of protection. At its fastest, 3I Atlas was traveling at over 60 kilometers per second. At such an extreme velocity, it would have flashed past any planet before gravity could have a significant effect on its trajectory. This incredible speed alone guaranteed that the probability of a collision was practically zero. Astronomers carefully calculated its minimum approach distance to every planet in the solar system to confirm that there was no risk. These calculations are a routine and vital part of planetary defense, but they also help us to understand how these interstellar objects behave as they navigate the complex gravitational environment of our solar system. Interestingly, while 3I Atlas never came near Earth, it did pass closer to the giant planets Jupiter and Saturn. As we've seen, these enormous gas worlds gave the traveler a few subtle gravitational tugs as it moved by slightly bending its path. By studying these gravitational encounters, astronomers can refine their models, making their predictions about the paths of future interstellar objects even more accurate. And though 3I Atlas itself will soon vanish back into the darkness of space, its brief harmless visit has provided important lessons. It reminds us that the cosmos is filled with these high-speed travelers and that future visitors may not pass so far away. This is why astronomers stress the importance of detecting these objects early, long before they reach their closest approach to the Sun. The next generation of powerful all-sky surveys, like the Vera C. Rubin Observatory, will soon be scanning the heavens more thoroughly than ever before. With these new eyes on the sky, we will be able to detect many more of these rare visitors from other star systems, and we will be able to do so much earlier, giving us more time to study them and to be certain that their paths pose no threat. For now, 3I Atlas stands as only the third confirmed interstellar object ever found. Its safe passage shows that not all cosmic wanderers are dangerous, but they all are fascinating messengers from the greater galaxy, each one carrying with it the secrets of a world beyond our own. One of the most defining, and for astronomers frustrating characteristics of interstellar objects is the brevity of their visit. Ordinary comets and asteroids that belong to our solar system can often remain visible for years, their long looping orbits bringing them back into view again and again. But interstellar wanderers like 3Y Atlas are very different. They appear suddenly from the interstellar darkness race across the inner solar system at incredible speeds and then vanish forever, their strange hyperbolic paths ensuring that they will never return. This creates a unique and urgent challenge for astronomers. They must act with incredible speed as every day, every hour matters. The window of opportunity to study these objects is fleeting, and if it is missed, it is gone forever. When 3I Atlas was first detected in December of 2019, it was already moving at an astonishing speed. It was still hundreds of millions of kilometers from the Sun, but it was closing fast. As it drew nearer, the Sun's light and heat began to work on its icy surface, causing some of its frozen gases to sublimate and form a faint glowing coma. This made the object brighter and easier to spot, but only for a short time. Its brightness peaked around the time of its perihelion in May of 2020. After that, as it began its long journey away from the Sun, its light began to fade rapidly. The Sun's warmth could no longer sustain its faint halo of gas and dust, and it quickly became too dim for all but the most powerful telescopes to see. In total, 3I Atlas was bright enough to be studied in detail for only a few short months. This incredibly brief period of visibility meant that astronomers had to coordinate a global campaign of observations, racing against time to collect as much data as possible from telescopes all around the world. Every single observation was precious. The short time that 3I Atlas spent in the spotlight is a vivid reminder of just how fleeting these discoveries can be. They move so quickly and travel such enormous distances that we often have only a matter of months or even weeks to study them before they are gone. This challenge is not just a matter of scientific curiosity, it also has implications for planetary defense. While the chances of an interstellar object striking the Earth are extremely small, their high speeds and unpredictable arrival times mean that early detection is crucial. By studying them carefully, even during their brief passages, scientists can better understand how often they appear, how they behave, and what kinds of risks they might one day pose. The fleeting glimpse we had of 3I Atlas also highlights the extraordinary value of every single interstellar discovery. Observing the physical, chemical, and orbital properties of an object that was born in another star system is a rare privilege. By examining its dust, its gas, and its structure, we are learning not just about this one cosmic traveler, but about the wider galaxy. What kinds of stars give birth to such wanderers? How are they changed by their long journeys through interstellar space? And what secrets about alien chemistry are hidden in their ancient frozen hearts? Studying the way dust behaves around an object like 3I Atlas gives scientists important clues about the nature of these interstellar comets. In our own solar system, comets are famous for their long glowing dust tails, which are created when sunlight warms their icy surfaces, causing frozen gases to sublimate and drag tiny dust grains into space. But 3I Atlas did not behave like a typical lively comet. Instead of producing a grand sweeping tail, its dust activity was faint, uneven, and difficult to detect. This puzzled astronomers and raised the question of whether interstellar comets are fundamentally different from those born in our own solar system. When the interstellar comet Borisov passed through our system in 2019, it displayed a bright and obvious dust tail. In contrast, 3I Atlas showed only a dim halo of dust so faint that even the world's largest telescopes struggled to see it. This difference suggests that interstellar comets are far more diverse than we imagined. The weak, ghostly dust halo of 3I Atlas suggests that it may not contain as much of the easily sublimated ices as a typical solar system comet. Instead, it could be made of more resistant materials, or its surface may have been hardened by its long exposure to cosmic radiation. This hardened crust could act as an insulating layer protecting the deeper ices from escaping easily. This would allow only a small amount of gas and dust to be released, creating a thin haze rather than a grand streaming tail. This weak outflow of dust also tells us something about the comet's possible origins. The presence of silicate grains rocky minerals in its faint coma suggests that 3I Atlas may have come from a planetary system where both rock and ice were mixed together. Perhaps it was once part of a larger differentiated body like a moon or a planetesimal that was shattered and ejected into deep space. The way its dust behaves reminds us that not all comets are created equal. Some, like those from our own Oort cloud, are rich in ices and flare up dramatically when warmed. Others, like 3I Atlas, may have traveled for so long that their surfaces have become crusted and their activity muted. This raises an exciting possibility. The nature of an interstellar comet's activity may be a direct reflection of its history, a clue to the environment of its home star system, and the duration of its long journey through the galaxy. Astronomers are still puzzling over the true nature of 3I Atlas. Is it simply another comet? Or could it be something far more unusual, a broken-off fragment from a much larger world? One of the most fascinating possibilities is that it is a planetesimal fragment. Planetesimals are the original building blocks of planets. In young star systems, these small rocky and icy bodies are constantly colliding and merging, gradually growing into moons and planets. But sometimes these violent interactions, or the gravitational pull of giant planets, can tear them apart. If 3I Atlas is indeed a shattered piece of a planetesimal, then we are seeing not just an ordinary comet, but a rare piece of the raw material of another planetary system, a piece that was ejected into the dark between the stars long ago. Several clues hint that this might be the case. First, its chemical makeup is unusual. While it contains the ices of a comet, it also contains a significant amount of rocky silicate minerals. This suggests it may have come from a larger, more complex body that had already undergone some degree of internal heating and differentiation, separating its rock from its ice. Such worlds are far more evolved than the simple, pristine ice balls that we think of as primordial comets. Second, its irregular shape and rotation are consistent with an object that has been violently broken apart. Third, its weak cometary activity suggests that its outer layers may have been scorched and weathered for eons, sealing off its deeper ice reserves. This makes it seem tougher and more resilient than a fragile, loosely bound comet. If 3I Atlas is truly a planetary fragment, then it was likely expelled from its home system during the chaotic early years of planet formation, when giant planets were migrating and scattering smaller bodies in their wake. Its path seems to point back to the star-forming regions of Carina and Scorpius, where countless young suns and their nascent planetary systems are being born. Perhaps it began its life in one of these crowded stellar cradles. To unlock more of its story, astronomers are continuing to study its reflective properties and its chemical signatures. If its outer layers are rich in complex carbon-bearing organic materials, it could mean it once belonged to a carbon-rich planetesimal, a type of body that is common in the cold outer zones of solar systems. If this is true, it would support the idea that we are looking at a tiny wandering fragment of a much larger broken world, a silent survivor from an ancient alien planetary system. So is it a comet, or is it an asteroid from beyond the stars? The answer, it seems, is that it may be neither, or perhaps a bit of both. Comets are typically icy bodies that release gas and dust when warmed, while asteroids are generally dry and rocky. 3I Atlas showed some faint comet-like activity, including a thin dust halo and the spectral signatures of water ice and carbon monoxide. and yet its activity was surprisingly weak and subdued compared to a classic comet like Borisov. This has led some astronomers to suggest that it is not a simple comet but a hybrid, a cosmic in-between object. This possibility is fascinating. Perhaps 3Y Atlas began its life as a comet in another star system, but was fundamentally transformed by its long journey through interstellar space. Billions of years of exposure to cosmic radiation could have baked its surface, creating a hardened, insulating crust that trapped most of its ices deep within its interior. Or perhaps it was born in a region of its home system that was transitional, a place where both icy and rocky materials were present, resulting in a body that was a natural hybrid from the start. Its hyperbolic, unbound orbit confirms that it is an interstellar wanderer, not a native of our solar system. Comets and asteroids from our own system are typically found in well-defined regions like the asteroid belt or the Kuiper belt. 3I Atlas belongs to neither of these families. It is a true drifter between the stars. The question of its identity continues to spark debate, a reminder of how much we still have to learn about the incredible diversity of objects that roam our galaxy. Each new visitor, with its own unique set of properties, is adding another piece to the puzzle, gradually building a clearer picture of the processes that shape worlds both here and in the vast, unexplored territory of other star systems. The long and lonely voyage of 3I Atlas from its unknown home system to our own is a story of incredible survival. The space between the stars is one of the harshest environments imaginable, a realm of intense radiation, extreme cold, and near-perfect vacuum. How did this small, fragile object manage to endure such a dangerous and unimaginably long journey? To understand its survival, scientists use sophisticated thermal models, computer simulations that predict how an object like 3I Atlas would react to the relentless challenges of interstellar space. One of the greatest threats is cosmic radiation. As it sailed through the void, it would have been constantly bombarded by high-energy particles that can alter its chemistry and erode its surface. This bombardment likely created the dark radiation-processed crust that seems to coat the object. But ironically, this very damage may have been its salvation. By forming a hardened, insulating layer on the outside, this crust could have protected the more fragile, volatile ices of its interior. Its survival also depended on its ability to maintain its thermal balance. In the deep cold of interstellar space, hundreds of degrees below, freezing its ices would have remained safely locked in their solid state. But when it approached our sun, the sudden increase in temperature could have caused a thermal shock, cracking and fracturing its surface. Its thick crust likely acted as an insulator, preventing a catastrophic breakup and allowing only a small, gentle release of gas and dust. Another factor is its irregular shape and rotation. A lopsided body heats unevenly, which could lead to localized bursts of outgassing rather than a global explosive release of its volatiles. This may explain why 3I Atlas appeared so faint and subdued compared to a more active comet like Borisov. But there is still much we do not know. Its long journey cannot have been entirely uneventful. Interstellar space is not truly empty. It is filled with giant molecular clouds, cosmic dust, and the remnants of ancient supernovae. It is highly likely that 3Y Atlas passed through some of these environments, each encounter leaving faint scars on its surface, subtle chemical and physical fingerprints that may one day help us to retrace its path. Even if the chance of a direct passage through another star system is low, it almost certainly passed through star-forming regions and dense stellar environments that quietly reshaped its surface. And that is why this object is so valuable. Its outer skin still holds the clues to this long and complex history. Its faint activity and thin halo of dust hint at a mixture of ices and organics that have been altered over uncounted ages. By studying these changes, we may be able to discover not only how it survived its journey, but also whether it once carried the whispers of other worlds on its surface, tiny traces of chemistry that were born in distant stellar nurseries. And this brings us to the question of its role in planetary defense. While 3I Atlas itself never posed a direct threat to Earth, Its sudden arrival is a powerful reminder that our solar system is not an isolated island, but is part of a larger dynamic galaxy through which objects are constantly moving. By studying its speed, its shape, its activity, and its trajectory, scientists can improve our early warning systems, create better methods for identifying cosmic threats, and develop new strategies for responding to them if one should ever be found on a collision course with Earth. Most of our current planetary defense efforts are focused on near-Earth objects, the comets and asteroids that are native to our solar system. But interstellar visitors like 3I Atlas present a completely new kind of challenge. They arrive from unknown directions, they travel at much higher speeds, and they give us far less time to prepare. The speed of 3I Atlas, over 60 kilometers per second at its peak, would make any attempt to deflect it with our current technology incredibly difficult. This is why early detection is so crucial. New observatories like the Vera C. Rubin Observatory will soon be scanning the skies more thoroughly than ever before, giving us a better chance to spot these fleeting visitors long before they reach their closest approach. The brief but harmless passage of 3I Atlas has shown us that not all interstellar wanderers are dangerous, but they are all fascinating messengers from the greater galaxy, each one a data point that helps us to understand the nature of these cosmic travelers and to prepare for a future in which their visits may become a more common and important part of our cosmic experience. The discovery of 3I Atlas is more than just a scientific curiosity. It is an invitation, a challenge to the future of space exploration. Its brief fleeting passage has ignited the imagination of scientists and engineers, sparking serious conversations about a goal that was once the stuff of science fiction, sending a spacecraft to chase down and study an interstellar visitor up close. While it was not possible to send a mission to 3I Atlas itself, its arrival has made us dream about a future in which we might be ready for the next one. The idea of sending a spacecraft to rendezvous with an object from another star system is thrilling, but it is also one of the most difficult technical challenges we have ever faced. The primary obstacle is speed. An object like 3I Atlas travels at speeds that are far beyond the capabilities of any spacecraft we have ever built. To catch such a runaway traveler would require a new generation of propulsion systems technologies that can achieve incredible velocities without carrying an impossibly large amount of fuel. One promising idea is the solar sail, an enormous ultra-thin mirror that is propelled by the gentle but continuous pressure of sunlight itself. A spacecraft with a large enough solar sail could accelerate slowly but steadily for months or even years, eventually reaching the speeds needed to catch an object that is racing between the stars. Another advanced option is ion propulsion, which uses electricity to accelerate charged particles to create a small but highly efficient thrust. A spacecraft with an ion engine could operate for years, gradually building up enough speed to match that of an interstellar wanderer. But no matter how powerful the engine's timing is everything. 3I Atlas was moving so quickly that by the time it was discovered and its orbit was confirmed, it was already too late to launch a mission. To have any hope of chasing down these visitors, we need to detect them much earlier years in advance. This is where the next generation of sky surveys like the Vera C. Rubin Observatory will be revolutionary. With their ability to provide earlier warnings, we could have enough time to prepare and launch a spacecraft on the perfect trajectory to intercept the next interstellar visitor. Such a mission would be long and arduous, lasting for many years, perhaps even decades. The spacecraft would have to be incredibly robust, capable of surviving the harsh radiation and extreme cold of deep space. But the scientific payoff would be immense. To fly alongside an object like 3I Atlas, to study its surface in detail, to analyze the gas and dust of its coma, and perhaps even to land on it and collect a sample, this would be a truly historic achievement. It would be our first direct contact with a piece of another solar system. The path of an interstellar object also holds deep clues about the larger dynamics of our galaxy. By carefully measuring its trajectory, we can test our understanding of how stars and gas clouds move and interact, and how the Milky Way's gravitational field shapes the paths of these wandering objects. 3i Atlas also reminds us that the Milky Way is not a static, unchanging place. It is a living, moving system, and every gravitational tug between its stars can tip the balance of a planetary system, sometimes ejecting whole worlds or cometary bodies into the great interstellar sea. 3i Atlas is a fossil, a preserved relic of this ancient chaos. Did it leave anything behind? As it rushed through our solar system, its surface was warmed by the sun, likely causing some of its ices to sublimate and release a faint trail of dust and gas. These microscopic fragments, the cosmic crumbs left behind by this interstellar wanderer, may now be drifting through our solar system, a tiny but precious addition to the cloud of cosmic dust that surrounds us. These particles are too small to see, but they are incredibly important. If we could one day collect and analyze this interstellar dust, we would have in our hands a direct sample of material from a faraway star system. Some of these dust grains may even carry complex organic molecules, the raw ingredients for life. This is why the path of 3i Atlas is so important. Every interstellar object we discover is a clue to a much larger puzzle. 3i Atlas may have come and gone in a brief flash, but the mysteries it has left behind and the dreams of future exploration it has inspired will continue to guide us as we seek to understand our place in the vast and interconnected tapestry of the galaxy. The journey of 3i Atlas through our solar system was more than just a fleeting astronomical event. It was a rare window into the grand sweeping dynamics of our Milky Way galaxy. Every interstellar visitor is a messenger, its path a story written in the language of gravity, a tale that reveals not just its own history, but the hidden rhythms of the galaxy itself. By carefully studying its motion, astronomers can begin to unlock the secrets of how objects travel between the stars, how the galaxy's immense gravitational field shapes their journeys, and how stars and planetary systems influence one another across the vast expanse of space. Most objects in our solar system are bound to the sun in closed repeating orbits. But 3i Atlas was different. Its hyperbolic path was a one-way ticket, a clear sign that it was not a member of our solar family, but a true interstellar nomad. The sun's gravity could bend its path, but it could not hold it. By measuring its speed and mapping its trajectory with incredible precision, astronomers can test and refine our most fundamental ideas about how stars move, how galaxies evolve, and how the cosmic forces govern the endless traffic between the stars. One of the first great lessons from 3i Atlas is about how the motions of stars can scatter objects across the galaxy. Its path suggests it may have come from the general direction of the star-forming regions in Carina and Scorpius. It is tempting to imagine that it was once part of a young planetary system there until a close encounter with another star or the gravitational influence of a giant planet flung it out into deep space. By tracing its path backward in time, and by comparing it with the known motions of the stars in that region, astronomers can begin to build a picture of the chaotic dance that governs young stellar nurseries. Its very high speed also tells us something important. It was moving far faster than a typical comet from our own solar system, suggesting that it was ejected with great force. This supports the idea that many of these objects are born in the violent early days of star systems. And by comparing its motion to computer simulations of how stars drift and migrate, astronomers can test and improve their models of how our Milky Way galaxy has evolved over billions of years. 3i Atlas also reminds us that the galaxy is not a static place. It is a living, moving system. Stars orbit the galactic center, giant clouds of gas flow and collide, and even the invisible hand of dark matter shapes the cosmic landscape. Every gravitational tug between stars can tip the balance of a planetary system, sometimes ejecting bodies into the great interstellar sea. 3i Atlas is a living fossil of that ancient chaos. And as astronomers tracked its speed and direction through our solar system, they also measured how it interacted with the sun's gravity. Its rapid passage confirmed that it came from a region of the galaxy where gravity's influence is weaker, far from the tightly bound zones of dense star clusters. This makes it an especially valuable test particle for probing how the galactic gravitational field influences wandering objects. On an even larger scale, 3I Atlas helps us to learn about the invisible matter that fills the spaces between the stars. As it glided through our solar system, scientists watched closely to see how its faint coma of gas and dust interacted with the solar wind and cosmic radiation. These subtle effects can reveal how dense the interstellar medium is, allowing us to build a kind of map of the Milky Way's hidden structure. Step by step, visitors like 3I Atlas are allowing us to uncover the conditions of the galactic ocean in which all stars, including our own, are floating. But is it possible that a visitor like 3I Atlas could be captured? Its one-way journey turned into a permanent stay. The challenge lies in its incredible speed. The gravitational pull of our solar system is simply not strong enough to grab hold of something moving so quickly. The process of gravitational capture is extremely rare. To trap an interstellar object in orbit, it would need to lose a tremendous amount of its kinetic energy. The best, though still highly improbable, chance for this to happen naturally would be if a massive planet like Jupiter could use its enormous gravity to tug on the speeding object at just the right angle and speed. But everything would have to be perfectly aligned, a cosmic coincidence of the highest order. And yet, even without being captured, 3I Atlas has given us something priceless. It is a time capsule from another star system. Its icy, rocky body contains materials that were formed around a distant star in a region of the galaxy far from our own. It carries with it a frozen, pristine sample of the building blocks of planets preserved across unimaginable stretches of time and space. By studying it even from afar, we are reading a cosmic letter that was written in another world. These interstellar objects are likely the broken pieces of larger bodies, the shattered remnants of moons or planetesimals that were cast out from their home systems long ago. Because they have never been subjected to the intense heat and chemical processing of our own inner solar system, they carry a kind of untouched purity. The traces of water ice and carbon monoxide that astronomers detected on 3Y Atlas are a sign that it was born in a faraway frozen region much like our own comets. And so, while capturing such an object may remain a distant dream, its fleeting visit has offered us an extraordinary gift, a brief but profound glimpse into the hidden chemistry and the ancient history of a star system beyond our own. The mysterious traveler. 3I Atlas is more than just a wandering rock. It is a cosmic messenger, a time capsule carrying secrets from a place and a time so remote that they challenge the limits of our imagination. What makes this object so extraordinary is the story that its atoms, its ices, and its rocks can tell us a story that was sealed billions of years ago in a star system far from our own. Long before our sun ignited, before the Earth had even begun to form, a vast cold cloud of gas and dust was drifting through another corner of the Milky Way. Within that cloud, the raw ingredients for new stars and planets were slowly gathering. And it was in such an environment that 3I Atlas was born. Billions of years ago, tiny grains of dust and ice began to stick together, gradually growing into a solid body. Then, through the chaotic dance of gravity and collisions, this small world was cast out of its home system, becoming a lonely traveler in the endless dark. Unlike the objects in our own solar system, which have been constantly heated and reshaped by the sun. 3I Atlas has spent most of its long existence in a state of deep freeze, its original composition perfectly preserved. That is what makes it so scientifically priceless. In its icy heart, it may still carry the chemical fingerprints of its birth cloud. By studying it, astronomers can peer into a chapter of cosmic history that is far older than anything we can study here at home. Imagine being able to analyze a sample of water or dust that has been frozen since the dawn of another planetary system. That is the opportunity that 3Y Atlas represents. If complex organic molecules like amino acids are present within it, it would be a powerful sign that the environment where it formed was friendly to the chemistry of life. These molecules are the essential stepping stones for biology, and if they exist on an interstellar visitor, it would strongly suggest that the universe is fertile with these ingredients. 3. I-Atlas could then be thought of as a cosmic courier delivering the raw materials of life across unimaginable distances. But it might be more than just a carrier of molecules. Its rocky materials, the silicates and minerals mixed in with its ice, hint that it may once have been part of a much larger body, perhaps a small moon or a planetesimal that was shattered in the violent youth of its parent system. If this is true, then 3I Atlas is not just a messenger, but a fossil from a broken world. Just as fossils on Earth tell us about the ancient life of our planet, this interstellar fragment could give us a glimpse into the geology of another solar system. Its dust, its minerals, and its ices could reveal what kinds of planets were forming around its star billions of years ago, and whether those planets were rocky like Earth, icy like Europa, or something entirely different. This idea is thrilling because it expands our vision of the kinds of worlds that may exist in our galaxy. By studying one tiny rock that has wandered into our neighborhood, we may learn about entire systems of planets that would otherwise remain forever invisible to us. For planetary scientists, objects like 3Y Atlas are a scientific goldmine, a chance to study material that does not belong to our solar system. Material that was formed under conditions we can only imagine. Every grain of dust, every trace of ice on its surface is a clue in a larger puzzle. And together, these pieces will help astronomers to build better models of how stars and planets form, evolve, and perhaps even host life. Perhaps the most profound aspect of 3I Atlas is how it connects to the ancient mystery of life's origins. For decades, scientists have debated whether life arose uniquely on Earth or whether its ingredients are sprinkled throughout the cosmos. Interstellar objects breathe new life into this debate. They suggest that the building blocks of life might not be limited to one small corner of the Milky Way, but could be scattered across the galaxy, carried by these wandering icy bodies. This is the heart of the panspermia hypothesis. The idea that life's essential molecules could travel from star to star, seeding new worlds. If 3I Atlas carries these prebiotic compounds, it would be powerful evidence for this idea. It would suggest that Earth may not be so special after all, but is simply one of many planets that were fertilized by these wandering couriers of life. The thought is staggering. Perhaps billions of years ago, an object like 3I Atlas struck the young Earth, delivering the very molecules that would later build DNA and proteins. And if it could happen here, why not elsewhere? The discovery of 3I Atlas is just the beginning. As our telescopes grow more powerful, we will find many more of these travelers. Each will have a different story to tell. And with every discovery, we will step closer to answering the great questions. How common are Earth-like worlds? How diverse are the planetary systems of our galaxy? And above all, how often do the seeds of life take root in the vast and fertile garden of the cosmos? The question of where life came from has haunted humanity for millennia. The idea of panspermia, that the seeds of life are everywhere, suggests that life's building blocks could travel from one world to another aboard cosmic travelers like comets and asteroids. This concept, once purely philosophical, has become a subject of serious scientific debate, especially with the discovery of interstellar objects like 3I Atlas. These visitors from other star systems are natural laboratories for testing this fascinating idea. When astronomers study these objects, they are looking for the chemical fingerprints of organic molecules, the carbon-based compounds that are the foundation of all life on Earth. If these molecules can survive the long, harsh journey through interstellar space, then panspermia becomes a plausible mechanism for spreading the potential for life across the galaxy. Our own solar system is filled with clues that support this idea. Comets. The icy bodies that originate in the cold outer regions of our solar system have been found to contain a rich variety of complex organic molecules, including amino acids, the building blocks of proteins. The NASA Stardust mission, which collected dust from the coma of Comet Wild 2, provided definitive proof of this. It showed that the raw materials for life are not unique to Earth, but can also form in the cold, dark vacuum of space. It is therefore highly likely that interstellar objects like 3I Atlas, which formed in a similar environment around another star, could also carry these life-giving molecules. In fact, they might be even better carriers, as their material could be more ancient and pristine, a frozen fossil of the chemistry that existed in another star system billions of years ago. If scientists can confirm the presence of these prebiotic materials on more interstellar objects, it would have enormous implications. It would mean that the processes that create the building blocks of life are not rare, but are likely happening all over the galaxy. The universe may be full of these raw materials, drifting through space, waiting for the right conditions, a warm, wet planet to combine and evolve into something more. This would completely change our perspective on our place in the cosmos. Earth would no longer be a lonely cradle of life, but just one of countless nurseries where the cosmic seeds of life have taken root. When astronomers observed 3I Atlas, they noticed a faint dust cloud surrounding it, likely containing the very organic materials that are so crucial for this theory. If these interstellar dust particles are common, they could play a huge role in the birth of new star systems, seeding the protoplanetary disks with the ingredients for life before the planets themselves have even fully formed. The discovery of water ice on 3I Atlas makes the picture even more compelling. Water is essential for life as we know it. If interstellar objects regularly deliver both water and organic compounds to young planets, they are providing all the necessary ingredients for biology to begin. One of the most interesting questions about these interstellar travelers is whether they remain intact on their long journeys. The fact that 3I Atlas survived its passage through our solar system is remarkable, but some of these objects may break apart, scattering their material across space. In this way, the destruction of an interstellar object might actually help to spread life's ingredients even farther, like a cosmic dandelion puffing its seeds into the wind. The study of objects like 3I Atlas touches on one of the greatest questions humanity has ever asked. Are we alone? If panspermia is real, then life may not be a uniquely terrestrial phenomenon. It could be a galactic process, with the potential for life constantly being sown across countless worlds. Some of those seeds may never find a place to grow, but others may land on planets with oceans and atmospheres where they could slowly evolve into living ecosystems. On Earth, life took billions of years to evolve from simple molecules to complex organisms. If the same processes are happening elsewhere, then the galaxy might be filled with planets teeming with life, perhaps even with intelligent beings who are looking up at their own night skies and wondering the same questions that we do. As 3I Atlas sped through our solar system, it faced a crucial test. Could it withstand the immense gravitational forces of our Sun without being torn apart? This question is vital for understanding the nature of these interstellar visitors. Their structural integrity, their ability to hold together under extreme stress, can tell us a great deal about their composition, their history, and their potential to survive the long and perilous journey between the stars. Tidal forces are a consequence of the way gravity varies across the length of an object. As 3I Atlas passed near our Sun, the side closest to the Sun felt a stronger gravitational pull than the side farthest away. This difference in force created a stretching effect, a tidal stress that could, in theory, rip a fragile object to pieces. And yet, as observations accumulated, it became clear that this visitor remained largely intact. Its cometary activity was minimal, a sign that its structure was holding together despite the powerful forces acting upon it. This suggested that 3I Atlas was sturdier than a typical loosely bound comet, perhaps composed of a more cohesive mixture of rock and ice. Its survival was a crucial piece of data indicating that some interstellar bodies are resilient enough to travel across the galaxy and enter new solar systems without immediately disintegrating. This observation has profound implications for our preparedness for future interstellar visitors. 3I Atlas was a harbinger, a glimpse of a larger cosmic reality in which objects from other star systems can and likely will cross our path more frequently than we once thought. Are we ready to detect, study, and perhaps one day even explore them? Advances in astronomical surveys like the ATLAS project that discovered this object are improving our ability to spot these fast-moving bodies. And the next generation of telescopes like the Vera C. Rubin Observatory will revolutionize this field, allowing us to identify interstellar objects earlier and track their paths with greater accuracy. Early detection is vital because these objects move at such extraordinary speeds that any mission to intercept them would require years of advanced planning and a new generation of high-speed propulsion technologies. The scientific value of these interstellar travelers cannot be overstated. They are messengers carrying the chemical signatures of distant star systems, offering unique insights into the environments where other planets are born. By analyzing their material, we can learn about the diversity of planetary systems, the universality of the building blocks of life, and the dynamic processes that shape our galaxy. The arrival of 3I Atlas has also forced us to confront new questions of planetary defense. While these objects are unlikely to collide with Earth, their high velocities make them a unique kind of potential threat, one that would be difficult to intercept. By studying them now, we can develop the strategies and technologies we might one day need to protect our planet. Perhaps the most exciting prospect of all lies in what we might learn from future visitors. Each object will tell a different story. And by piecing together these stories, we will gradually build a richer and more complex picture of our place in the cosmic tapestry, a picture in which the stars are no longer just distant points of light, but tangible destinations for our curiosity and our exploration. Why do we search? The question itself is a fundamental current of the human spirit, an ancient and persistent driver of our species, as primal as the need for food or the instinct to build shelter. It is the same impulse that led mariners to sail beyond the edge of the known world, not merely for conquest or for gold, but for the raw, unfiltered knowledge of what lay beyond the horizon. It is the restless curiosity that fuels the engine of science, the relentless urge to illuminate the quiet voids of our understanding with the light of discovery. We turn our gaze to the stars and ask a question that has echoed through millennia of human thought. A question at once profoundly scientific and deeply personal: are we alone? This is not merely a search for biology, for microbes clinging to life in a subterranean ocean or lichens spreading across a frozen rock. It is a search for biology that has awakened, for matter that has become clever enough to organize itself into a mind capable of contemplating the universe that spawned it. If we were to find such a civilization, the implications would be staggering. A shockwave that would ripple through every aspect of our culture, our philosophy, our very sense of self. The detection of a single, unambiguous, artificial signal would answer 1,000 existential questions in an instant. It would tell us that life is not a cosmic fluke, that intelligence is not a singular, terrifying accident, and that survival on a galactic timescale is, at least, possible. It would reframe our entire story, transforming us from cosmic orphans into the newest members of a galactic community. The search for extraterrestrial intelligence is a peculiar and noble form of science, one that operates outside the familiar textbook method. It is not a process of proposing a hypothesis and then attempting to falsify it. You cannot, with any amount of data or logic, prove the negative on this scale. You cannot demonstrate that intelligent life is not out there. The vastness of the cosmos and the depths of time make such a proof impossible. You can only do one thing. You can only discover that it is. This is the nature of discovery science. It is a patient vigil, a long listening. And on one quiet summer night, for a fleeting 72 seconds, it seemed as if that vigil had ended. A signal arrived. A whisper from the void, so powerful and so perfectly formed that it defied all natural explanation. It was not a message in a human sense, not a string of translatable words, but a sequence of 50 numbers and letters printed out on a continuous sheet of paper. A ghost from a bygone era of computing. Yet it remains the most profound and tantalizing clue humanity has ever received. 6. E. Q. U. J. 5. It appeared once, a transient, focused beam from an unknown source in the constellation Sagittarius, and was never heard from again. It has become an artifact of scientific folklore. A single, unexplained data point that continues to haunt the long silence of the search. It was the strongest signal ever recorded, an enormously powerful, narrow-band transmission that looked exactly like what we were looking for. And in its wake, it left a beautiful, aching mystery, a testament to the fact that sometimes the most compelling truths are found not in what we know, but in what we can never fully explain. The universe speaks in a language of light, but our eyes, the primary instruments of our perception, are attuned to only a tiny fraction of its vast and complex vocabulary. We are most familiar with optical astronomy, the ancient science of capturing visible light with telescopes to magnify distant objects. It is a practice born from the first moment a human ancestor looked up and wondered at the points of light scattered across the darkness. But the visible spectrum, that beautiful rainbow of colors our brains are wired to interpret, is an astonishingly narrow sliver of the full range of cosmic expression. The electromagnetic spectrum stretches from the high-energy fury of gamma rays and X-rays, the violent signatures of exploding stars and matter-devouring black holes, down to the low-energy, pervasive hum of infrared and radio waves. To see only invisible light is to walk through a vibrant, bustling metropolis while wearing blinders and earplugs, aware only of the sliver of reality directly in front of you, oblivious to the rich, layered tapestry of life and sound unfolding all around. Radio astronomy is the art of removing those blinders, of tuning our senses to the invisible chorus of the cosmos. Every star, every galaxy, every swirling cloud of interstellar gas produces energy across this entire spectrum. And the radio end holds a wealth of information that optical light cannot convey. It is in these long, low-energy waves that we can perceive the universe in a different state, hearing the hum of its fundamental processes, the echoes of its creation, rather than just seeing the flash of its brightest, most energetic moments. This ability to listen to the hidden universe was born in the early 1930s, when a scientist named Carl Jansky, working for Bell Labs, stumbled upon one of the most significant discoveries in the history of astronomy. He had built a large, rotating antenna, a contraption that looked like a skeletal Ferris wheel, to track the source of the persistent static that interfered with transatlantic radio communications. As he meticulously tracked the noise, he found that it rose and fell on a cycle of 23 hours and 56 minutes, the exact length of a sidereal day. The time it takes for the Earth to complete one rotation relative to the distant stars. He had discovered that the hiss was not coming from Earth, but from the heavens. He had pinpointed its source to the dense, bright center of our own Milky Way galaxy. For the first time, humanity had an ear to the cosmos, and the sky was not silent. This monumental discovery, however, was slow to ignite a revolution. It was a radio engineer from Wheaton, Illinois, a man named Grote Reber, who truly carried the torch of this new science. In his own backyard, with a 30-foot dish antenna he designed and built himself. Reber spent a solitary decade as the world's only active radio astronomer. Night after night, he painstakingly scanned the Milky Way, producing the first ever maps of the radio sky. His work was a labor of pure passion, laying the foundation for a new branch of science, and his homemade antenna became the conceptual blueprint for the colossal radio telescopes that would follow. The Second World War, for all its devastation, was a catalyst for incredible technological advancement, particularly in electronics and radar. In the war's aftermath, as nations began to rebuild, a new era of scientific ambition took hold. The United States, locked in the early stages of the Cold War and the space race, was eager to invest in fundamental science, to push the boundaries of knowledge and assert its technological prowess on the world stage. It was an era of big thinking, of moonshots and massive engineering projects. Unprecedented amounts of money flowed into building the tools of discovery, from particle accelerators that could probe the heart of the atom to giant telescopes that could look back to the dawn of time. It was in this fertile climate of scientific optimism that John Krause, a professor of electrical engineering at The Ohio State University, saw an opportunity to realize a long-held dream. He had been captivated by Jansky's discovery as a young man and inspired by Grote-Reber's pioneering work. During the war, he had made significant contributions to the development of radar, but his passion remained fixed on the cosmos. He dreamed of building a radio telescope of unprecedented scale, an instrument capable of not just listening to the Milky Way, but of conducting a comprehensive, definitive survey of the entire radio sky. He was an inventor as well as a scientist. He developed a unique, corkscrew-shaped antenna, the helical antenna, a design that would later prove essential for satellite communication. In 1952, with the help of his students, he built a small array of these antennas on a patch of university farmland. The survey was a success, but it only served to whet his appetite for something grander. He knew that to truly map the heavens, he needed an instrument of breathtaking size. His initial plans were almost fantastical, envisioning a telescope spanning 2,000 feet. Funding, as is so often the case in the pursuit of pure knowledge, was a limiting factor. His grand plans were scaled back, first to 720 feet, and then finally to a still massive 360 feet for the main parabolic reflector. In 1956, he secured a 20-acre plot of land and a grant from the National Science Foundation. The Ohio State University Radio Observatory was born, and with it, the ambitious project to build the great telescope that would affectionately come to be known as the Big Ear. The construction of the Big Ear was a monumental undertaking, a 5-year saga of ingenuity born from profound financial constraints. John Krause's grant was modest, far too small to hire a professional construction firm for a project of this magnitude. So, he turned to the most dedicated and affordable labor force he could find, his own volunteer graduate students, from 1956 to 1961. They toiled on the Ohio farmland, a small team of young scientists and engineers slowly bringing his unique, unconventional design to life. It was a telescope built not for elegance or for precision steering, but for one singular purpose: to be the most sensitive listening device on the planet for the least amount of money. The final structure was a marvel of minimalist engineering, a sprawling, static machine the size of 3 modern football fields. Its foundation was a vast, flat ground plane of aluminum mesh, 3 acres in extent, shimmering like a metallic lake. At one end stood a massive, curved parabolic reflector, fixed to the ground. At the other, a flat, tilting reflector, which could be adjusted to change the telescope's declination, its up and down aim into the heavens. Out in the middle of the aluminum field sat the feed horns, 2 large, scoop-like structures pointed at the parabola, designed to funnel the focused radio waves into the receivers. Unlike the sleek, steerable dish antennas of today, the Big Ear was largely immobile. It could not pan left or right to track an object across the sky. Instead, it relied on the steady, predictable, and free of charge rotation of the Earth to do the work. The operators would set the tilt of the flat reflector to a specific angle, and then, for 24 hours, the Earth itself would turn the telescope, sweeping its narrow beam across a thin, continuous strip of the sky. After a few days of patient observation, they would adjust the angle by a fraction of a degree and begin painting a new strip in this patient, methodical, and economical way. Over the course of years, they planned to create the first comprehensive map of the entire visible radio sky. When it was finally completed and brought online in the early 1960s, the Big Ear was one of the largest and most sensitive radio telescopes on Earth. Its initial purpose was not the speculative search for alien civilizations, but the foundational work of astronomical surveying. In those early days of the field, radio astronomy was still a young science, a frontier just beginning to be explored. While other astronomers had used smaller, more agile dish antennas to study specific stars or galaxies in detail, no one had yet undertaken a comprehensive all-sky survey to catalog the myriad sources of radio emission. The Big Ear's team, led by Krauss, were like the cartographers of old, charting a new, invisible continent. For the next decade, using an IBM computer with a now laughably small 16 kilobytes of memory, they meticulously collected, processed, and analyzed the data streaming from their giant instrument. The result was the Ohio All-Sky Survey, a monumental achievement in astronomy. They created a catalog of 20,000 cosmic radio sources, effectively doubling the number known to science at the time. They produced vast, detailed maps of the radio sky, a resource that would prove invaluable to astronomers around the world for decades to come. In the course of their survey, they discovered some of the most distant objects ever observed by any telescope, quasars whose light had traveled for 12 billion years to reach them, offering a precious glimpse back to the universe's infancy, not long after the Big Bang itself. It was a period of profound and fruitful scientific contribution, a successful chapter that firmly established the Big Ear as a major instrument of discovery and a testament to the vision of its creator. But as the 1970s dawned, the scientific landscape began to shift. New, more advanced, and more expensive telescopes were being built, and the National Science Foundation, facing ever-present budget constraints, made the difficult decision to terminate funding for the aging Big Ear. In 1972, the official survey came to an end. The closure of one chapter, however, marked the beginning of another, one that would etch the Big Ear's name into history for a reason no one, not even its visionary builders, could have possibly predicted. Deep in the rolling, verdant hills of West Virginia, nestled within a valley deliberately shielded by the Allegheny Mountains, lies the Green Bank Observatory. It is a place of intentional, almost sacred quiet. Here, the air is not just clean of pollutants, it is electronically pure. By an act of Congress, the surrounding region is a national radio quiet zone, a 130,000 square mile bubble of silence, where the pervasive electronic cacophony of modern technology, cell phones, Wi-Fi, microwave ovens, even gasoline-powered cars is either heavily restricted or banned outright. This electronic tranquility is not a quaint preference. It is an absolute scientific necessity. Because Green Bank is home to some of the most sensitive radio telescopes in the world, including the magnificent Robert C. Byrd Green Bank Telescope, the largest fully steerable radio dish on the planet. The story of Green Bank, like that of the Big Ear, begins in the optimistic, ambitious post-war era of the late 1950s, as radio astronomy blossomed from a niche curiosity into a legitimate field of science. The United States recognized the need for a national observatory, a central facility that could house instruments larger, more powerful, and far more expensive than any single university could hope to build. The search began for the perfect location, a site that could provide the ultimate listening environment. The criteria were demanding a place with a very low population density, free from the electronic noise of power lines and cities, and ideally shielded by natural topography. After surveying dozens of sites up and down the East Coast, they found their ideal location in the secluded, isolated valleys of Green Bank. In 1957, the site was dedicated, and the first telescopes began to rise from the ground, great metal structures aimed at the silent heavens. Green Bank quickly became a pilgrimage site for the world's leading radio astronomers. They were drawn by the promise of access to the biggest and best instruments, and by the legally protected radio silence that allowed them to listen to the faintest, most distant whispers from the cosmos. Among them were a few bold scientists interested in a new, more speculative, and to some, more profound application of radio astronomy, the search for extraterrestrial intelligence, or SETI. One of these pioneers was a brilliant young astronomer named Frank Drake. In 1960, using one of Green Bank's then new 85-foot telescopes, he conducted the first modern SETI experiment. He called it Project Ozma. For 200 hours over the course of several months, he painstakingly pointed the telescope at two nearby, sun-like stars, Tau Ceti and Epsilon Eridani, patiently listening for any signal that bore the unmistakable hallmarks of intelligent design, a signal that was narrow-band, focused, and artificial. He found nothing but the quiet hum of the cosmos, but the act of looking was itself a revolutionary step. It took the search for alien life out of the realm of science fiction and placed it firmly within the domain of legitimate, albeit long-shot, scientific inquiry. A year later, in 1961, Drake convened a small, now legendary meeting at Green Bank. He brought together a handful of the world's brightest minds, astronomers, chemists, biologists, and even a young, charismatic astronomer named Carl Sagan to have the first serious, structured discussion about the prospects for finding intelligent life elsewhere in the universe. In preparation for this historic meeting, Drake sought a way to frame the enormous problem, to give the discussion a rational, scientific structure. He began to jot down on a piece of paper the series of factors that would, in sequence, determine the number of detectable civilizations in our galaxy. He started with the rate of star formation. He then multiplied that by the fraction of those stars that have planets. Then, the average number of planets per star that could potentially support life. Then, the fraction of those planets on which life actually arises. Then, the fraction of life-bearing planets on which intelligence evolves. Then, the fraction of intelligent civilizations that develop technology capable of interstellar communication. And finally, he added the most enigmatic and sobering variable of all, L, the length of time such a communicating civilization might survive. He strung these 7 factors together into a simple-looking but profoundly complex formula that would become known as the Drake equation. It was never meant to provide a definitive answer. In 1961, most of its terms were complete unknowns, educated guesses at best. Its true purpose was to serve as a roadmap for the search, a powerful tool for organizing our ignorance and identifying the key questions we needed to answer to move forward. The equation itself is a beautiful and timeless piece of scientific reasoning. Decades later, it remains the fundamental framework for thinking about life in the universe. In the years since Drake first wrote it down, we have begun to make real progress on the early terms. Thanks to missions like the Kepler Space Telescope, we now know that planets are not rare, but common, with most stars in our galaxy hosting planetary systems. We are on the verge of being able to identify potentially habitable, Earth-like planets. But the later terms of the equation, those concerning the emergence of life, the evolution of intelligence, and especially the longevity of civilizations, remain shrouded in deep uncertainty. The final term, L, is a mirror held up to ourselves. We have only one data point for a communicating civilization, our own. How long will we last? A few centuries, a few millennia, a million years? The answer to that question dramatically alters the final result of the equation, determining whether the galaxy is teeming with active, ongoing conversations or is, instead, filled with the silent ruins and faint echoes of countless civilizations that have risen, shone brightly for a time, and then vanished. The Drake equation tells us, with chilling clarity, that the universe could be silent either because life is exceptionally rare, or because intelligent life is, as a rule, tragically self-destructive. With the closure of its official survey and the termination of its federal funding, the Big Ear Observatory faced an uncertain future, a slow decay into obsolescence. But a new purpose was emerging from the fringe of mainstream astronomy, inspired by the very questions being asked at places like Green Bank. Bob Dixon, the assistant director of the observatory, had attended a NASA-sponsored conference on Project Cyclops, a hugely ambitious conceptual design for a massive array of radio telescopes that would be dedicated to the search for extraterrestrial intelligence. The final report from that conference circulated widely, influencing a generation of young astronomers and solidifying the scientific case for a serious, sustained search. Dixon returned to Ohio with a bold idea. They had a world-class radio telescope, an instrument of immense sensitivity, sitting idle. They had a dedicated staff of engineers and students, a team of volunteers willing to continue the work out of pure passion. They could reconfigure the Big Ear, tune it for a new kind of signal, and dedicate it to the most profound search in human history. It would become the first large telescope in the world dedicated full-time to SETI, with no external funding, relying solely on the passion and ingenuity of its small team. They began the arduous task of transforming the instrument. The original all-sky survey had utilized wideband receivers designed to pick up the broad, chaotic, and noisy emissions of natural cosmic objects. But the search for an intelligent signal required a completely different approach. The prevailing theory, then as now, was that any civilization attempting to communicate across the vast, noisy distances of interstellar space would use a narrowband signal. Natural sources are like a shouting crowd, broadcasting across a wide range of frequencies, creating a cacophony of cosmic static. An artificial signal, however, would be like a single, clear, pure note played on a flute, a focused transmission at a single point on the radio dial, specifically designed to stand out against the overwhelming background noise of the universe. The team at Big Ear designed and built a new 50-channel receiver, a bank of 50 separate, highly sensitive radios, each tuned to a slightly different, very narrow frequency band, all centered around the 1,420 megahertz hydrogen line. In December of 1973, the Big Ear's second life, its true calling, began. For the next 4 years, it patiently scanned the skies, its great metallic ear turned to the heavens, listening for a single, clear note in the grand, cosmic symphony. On the clear, warm evening of August 15th, 1977, the Big Ear was performing its silent, automated, and lonely vigil. The great flat reflector was tilted to its preset angle, and the Earth's steady rotation was slowly sweeping the telescope's dual beams across a strip of the night sky, passing through the dense star fields of the constellation Sagittarius. No one was at the observatory. The entire process was automated. A ghost in the machine. Incoming radio waves were collected by the giant reflectors, funneled into the feed horns, and processed by the IBM computer. The intensity of the signal on each of the 50 channels was measured every 10 seconds, translated into a simple alphanumeric code, and then diligently printed out, line by line, on long, continuous sheets of perforated paper. The system was a model of efficiency, designed to be run by a small team of volunteers with minimal oversight. A few days later, Jerry Amon, a volunteer professor from a nearby university, made his routine trip to the observatory. He collected the reams of printouts from the past several days and took them home for analysis. It was a methodical, often tedious task he performed several times a week, a quiet contribution to a grand search. After dinner, he would sit down at his kitchen table with the stacks of paper and begin the patient process of scanning the 50 columns of data. His eyes trained to look for anything out of the ordinary, any deviation from the expected background noise. Most of what he saw on those printouts was statistical noise. The expected random fluctuations of the cosmic microwave background, occasionally punctuated by the jagged, erratic spikes of recognizable interference from terrestrial sources like aircraft or distant military radar. It was a search for a needle in a cosmic haystack. But as he worked his way through the data from the night of August 15th, his eyes caught a sequence in one of the columns that made his heart stop. It was a pattern that was anything but random. In a single, narrow-frequency channel, he saw the data begin to climb. The printout showed a 6. Then, on the next 10-second line, the intensity jumped to an E, the code for 14. Then it leaped to a Q, then a U, the code for 30, then a J, and finally a 5, before dropping back to baseline. The numbers and letters formed a steep, perfect crescendo, peaked dramatically, and then descended in a near-perfect mirror image of their ascent. It was the exact signature they had been hoping for, the unmistakable profile of a powerful, continuous celestial source passing directly through the center of the telescope's narrow beam. The intensity was staggering. At its peak, the signal was over 30 times stronger than the average background noise. It was, by an enormous margin, the most powerful and coherent signal the Big Ear had ever detected. Amon knew immediately, with the certainty of a trained analyst, that this was not interference. Terrestrial interference is messy, erratic. It pulses on and off, creating jagged, ugly spikes in the data. This signal was smooth, elegant, a perfect Gaussian bell curve that precisely matched the theoretical shape of the telescope's antenna pattern as it scanned across a fixed point in the sky. It was as if something out there, in the direction of Sagittarius, had been waiting patiently for the Big Ear's gaze to sweep past it. In that singular moment of discovery, overwhelmed by the profound and almost terrifying implications of what he was seeing, Jerry Amon grabbed a red pen, circled the incredible alphanumeric sequence 6EQUUJ5 on the printout, and in the margin, he wrote a single, emphatic, and now legendary word wow. The discovery of the wow signal triggered an immediate, intense, and private investigation. Amon, Krauss, and Dixon began the rigorous process of scientific due diligence, their excitement tempered by a deep-seated skepticism. Their first and most important task was to try to eliminate every possible alternative explanation before even considering the extraordinary one. Could it have been an equipment malfunction? This seemed highly unlikely. The signal was detected with pristine clarity on only one of the 50 channels. A systemic glitch or malfunction would almost certainly have affected multiple channels at once, or produced a less coherent pattern. Could it have been a known natural source, like a planet, a star, or a distant galaxy? Krauss, the observatory's director, meticulously checked astronomical charts and catalogs. There were no known celestial objects in that specific patch of sky capable of producing such a powerful, and more importantly, such a narrow-band signal. Natural cosmic sources broadcast their energy across a wide range of frequencies. This signal was sharply focused. Could it have been an Earth-orbiting satellite? This was a more plausible, though still highly improbable, explanation. The signal was detected at a frequency of 1,420 megahertz. This frequency, known as the hydrogen line, is a universally significant frequency in astronomy because it is the natural emission frequency of neutral hydrogen, the most abundant element in the universe. Because of its profound scientific importance, this band of the radio spectrum is internationally protected by law. All terrestrial and satellite transmissions are strictly forbidden on it. For a satellite to be broadcasting illegally on this protected frequency was possible, but unlikely. Furthermore, a satellite would be moving across the sky at its own speed and trajectory. For its motion to have perfectly mimicked the steady, slow rotation of the Earth and produce that flawless 72-second-long bell curve was a statistical improbability of astronomical proportions. Could it have been a deliberate hoax? Only Amon and Dixon had the technical access to the computer systems to manipulate the data in such a way. Both knew, with absolute certainty, that they had not. As they systematically ruled out each conventional explanation, the extraterrestrial hypothesis, as wild as it seemed, became more and more compelling. But there was a critical, confounding, and ultimately ambiguous piece of the puzzle. The Big Ear, with its unique and economical design, actually had two feed horns, two ears listening to the sky, situated side by side. This meant it had two beams. Any continuous celestial source, like a distant star or galaxy, would pass through the first beam. And then, approximately 3 minutes later, as the Earth continued to turn, it would pass through the second beam, producing two identical signals, separated by that 3-minute interval. This dual beam system was a brilliant, built-in mechanism for verifying signals and rejecting local interference. The wow signal appeared with incredible, undeniable clarity in the first beam. But when the team, with bated breath, checked the data from the second beam, there was nothing, only silence. This fact added another profound layer of mystery to the event. For some, this was definitive evidence against an extraterrestrial origin, suggesting some sort of transient, one-off fluke, or a previously unknown type of terrestrial interference. For others, however, it made the signal even more exciting. It implied that the source was not a continuous, steady beacon. It had turned on, or perhaps its narrow beam had swept past us. During the 72 seconds, it was in the view of the first horn. And then it had turned off, or its beam had moved on, before the second horn could catch it. A natural signal would not behave this way. An artificial signal, a deliberate, transient ping from a distant intelligence, very well might. For the next month, the Big Ear was repeatedly and deliberately aimed at that same patch of sky, listening intently for a repeat performance. For 70 days after that, it continued the vigil. Nothing was ever heard again. The signal had come and gone, leaving behind a single, unverified, and utterly perplexing artifact, a ghost in the data, a question mark hanging in the cosmos. The wow signal quickly became a legend in the small, dedicated, and often maligned community of SETI researchers. It was a tantalizing glimpse of what might be possible, a ghost that fueled both hope and fierce debate for decades to come. But the broader scientific community, by necessity, remained deeply skeptical. A single, unrepeatable event, no matter how intriguing, does not constitute the extraordinary proof required for such an extraordinary claim. The scientific method demands verification without a second detection. The wow signal was destined to remain an anomaly, a curiosity. The search required more than just listening. It required a robust framework for thinking, a way to quantify the vast, almost incomprehensible uncertainties involved. This is where Frank Drake's pioneering work at Green Bank provided the essential intellectual context. His equation, while not providing any concrete answers, served as a powerful tool for illustrating the immense scale of the challenge. To find a verifiable signal, a chain of countless low-probability events had to align perfectly. A planet had to exist in the right place, around the right kind of star. Life had to arise from non-life. That life had to evolve intelligence. That intelligence had to develop a technological civilization. That civilization had to not only choose to broadcast powerful signals into space, but it also had to survive its own technological infancy long enough for its signal to cross the immense, silent void and arrive at our solar system at the precise moment our telescopes happen to be pointed in the right direction, tuned to the right frequency. The search, as the Drake equation made starkly clear, was like searching for a single, specific, marked grain of sand on all the beaches of the entire world. And yet the possibility, however remote, was too profound, too central to our own quest for meaning, to ignore. The story of the WOW signal also inspired a different, more personal kind of search, one driven not by large institutions and government grants, but by individual passion and relentless curiosity. Robert Gray, a data analyst and amateur astronomer from Chicago, read about the signal in a small magazine published by John Krause in the late 1970s. He was utterly captivated by the mystery. He traveled to Ohio, visited the Big Ear, examined the original data printouts, and became convinced that the signal was a genuine candidate worthy of a serious, sustained follow-up. In the early 1980s, in a modern echo of Grote Reber's backyard pioneering, he built his own radio telescope, a 12-foot dish, and began his own, decades-long, largely solitary quest to find the signal again. He later gained access to professional telescopes, from the Oak Ridge Observatory at Harvard to the Very Large Array in the New Mexico desert, meticulously and patiently searching the small patch of sky where the signal had originated. He found nothing, but his lonely vigil highlights a crucial and often overlooked aspect of the WOW signal's enduring legacy, despite its fame and its tantalizing characteristics. The professional astronomical community never mounted a sustained, long-term effort to redetect it. The resources of big science are finite, and in a competitive field where progress is measured by verifiable, repeatable, and publishable results, a one-time, unconfirmed anomaly, no matter how spectacular, is often relegated to the status of a curiosity, a fascinating but ultimately unproductive footnote in the annals of science. Most professional SETI experiments, then and now, are designed to survey as many stars and as many frequencies as possible, spending only minutes, or even seconds, on any given target. The strategy is to cast the widest possible net in the cosmic ocean, but this entire approach is predicated on a significant assumption that a signal, if it exists, will be a continuous, unwavering beacon, shining brightly for anyone who happens to look. But what if that assumption is wrong? What if a truly advanced civilization, mindful of the colossal energy expenditure required for interstellar communication, would choose a more efficient, more patient strategy? The scenario of a directed, sweeping beam, like a cosmic lighthouse, offers a compelling and elegant explanation for the transient nature of the WOW signal. A civilization might not waste the astronomical amount of power required to broadcast a signal in all directions at once. Instead, they might use a powerful, highly focused antenna to ping a long, pre-compiled list of potentially life-bearing planets, targeting each one sequentially for a short duration before moving on to the next. They might send a pulse our way once a day, or once a year, or once a millennium. Our 72-second detection in this scenario would have been an incredible, almost impossible stroke of luck. A fleeting moment when our humble telescope happened to be looking in the right direction at the exact instant that an ancient, sweeping beam of light washed over our planet. This possibility completely reframes the meaning of the long silence that followed. It is not necessarily evidence of the signal's non-existence, but perhaps evidence of a different kind of communication strategy, one far more patient, more deliberate, and more energy efficient than our own. It transforms the search from a passive act of listening for a constant, steady drone into an active and far more challenging game of cosmic timing, waiting for a fleeting whisper that may not come again in our lifetimes, or even in the lifetime of our civilization. The wow signal, viewed in this light, is not just a mystery to be solved, but a profound and humbling lesson in the potential nature of interstellar contact. It suggests that a conversation across the stars may not be a dialogue as we understand it, but a series of isolated, monadic messages, separated by gulfs of time and space so vast they challenge our very definition of what it means to communicate. The eventual fate of the Big Ear telescope is a poignant and perhaps inevitable epilogue to the story of its greatest and most enigmatic discovery. For 25 years after the detection of the WOW signal, it continued its dedicated SETI program, becoming, in the process, the longest-running, full-scale SETI project of its time. A feat recognized by the Guinness Book of World Records, it accomplished this almost entirely without federal funding. A remarkable testament to the unwavering dedication and passion of its small volunteer staff. But in the mid-1990s, the quiet patch of Ohio farmland on which it stood had become valuable real estate. Engulfed by the relentless spread of suburban development, a developer purchased the property with plans to expand an adjacent 9-hole golf course into a full 18-hole course and to build 400 new luxury homes. There was a public outcry, a desperate attempt by scientists and space enthusiasts to save the historic instrument. But the university, facing the prospect of long and expensive legal battles, chose not to fight. The telescope, in the eyes of many, had become obsolete. Its main reflector was frozen in place, its analog technology superseded by newer, more flexible, and more powerful digital instruments. In 1998, the demolition crews arrived. The giant metal structures were torn down, the vast aluminum ground plane ripped up and sold for scrap, where a massive, sensitive ear once listened to the deepest secrets of the cosmos. There are now manicured fairways, sand traps, and the quiet streets of a housing development. The demolition of the Big Ear is a stark and unsentimental symbol of the relentless nature of scientific and societal progress. Instruments, no matter how historic or significant, eventually outlive their usefulness. Science moves on. But there is a tragic and beautiful irony in its demise. If the WOW signal is ever confirmed to be a genuine extraterrestrial broadcast, the spot on Earth where humanity first heard the voice of another world will be nothing more than the 7th hole of a golf course. The end of the Big Ear, however, was not the end of the search. The torch was passed to a new generation of observatories, more powerful and more sensitive than John Krause could have ever dreamed. The primary heir to this legacy is the Green Bank Observatory. After facing its own existential funding crises in the early 2010s, when the National Science Foundation announced plans to divest from the facility, Green Bank found a new partner and a new, revitalized purpose. In 2015, a privately funded $100 million initiative called Breakthrough Listen was launched by the billionaire Yuri Milner, with the enthusiastic endorsement of scientists like Stephen Hawking and Frank Drake. The project's goal is to conduct the most comprehensive and sensitive search for extraterrestrial intelligence in history. To do this, it secured a significant portion of observing time on the world's most powerful radio telescopes, with the Green Bank telescope at the very heart of its operations. The search that began with Frank Drake's modest 2-star Project Ozma has now evolved into a massive, data-intensive, global operation, Breakthrough. Listen scans millions of stars and billions of radio channels simultaneously, generating more data in a single day than all previous SETI projects combined over 50 years. The technology is vastly more sophisticated. The scope of the search is orders of magnitude larger. But the fundamental question remains exactly the same. We are still listening for a pattern in the noise, a single, clear, artificial note that stands apart from the deep, chaotic static of the cosmos. We are, in essence, searching for our own wow signal, but this time, with instruments powerful enough to follow up immediately, to verify, to confirm, and to finally, perhaps, answer the question. And so we continue to listen. We persevere through the long, profound silence, through the persistent skepticism and the perennial funding challenges, because the stakes are simply too high to stop. The search is a strange and difficult kind of science, a field that demands the patience of a saint and the hide of a rhinoceros. A field where a lifetime of dedicated work may yield no positive results, where the only guarantee is the search itself. But it is driven by something deeper and more resilient than the scientific method alone. It is driven by a deep, innate, and universal human need for context. A profound desire to understand our own existence by learning if we are a singular, inexplicable miracle, or part of a vast, ancient, and unfolding cosmic community. The discovery of a single, verifiable signal would be a true inflection point in the history of our species. It would instantly and irrevocably transform our perspective, uniting every person on the planet with the shared, stunning knowledge that we are not alone. It might, in time, grant us access to knowledge far beyond our own, the accumulated wisdom of a civilization that has successfully navigated the same existential crises we now face. But even the silence, the great cosmic silence, has meaning. The Fermi paradox: if intelligent life is common, then where is everybody hangs over the entire endeavor like a shadow. The silence could mean that intelligent life is exceptionally, tragically rare. It could mean that we are, for all practical purposes, alone in our galaxy. It could mean that we are the first. And if that is the case, it bestows upon us an almost unbearable responsibility to survive, to cherish the fragile spark of consciousness we hold, and to become the voice that one day breaks the silence for others. We search because we are lonely. We search because we are hopeful. We search because the universe is vast and filled with unimaginable possibility, and the simple act of listening, of turning our collective attention outward to the great, quiet, and mysterious expanse, is one of the most profound and noble expressions of our own intelligence. It is, in the end, an act of faith in the possibility of connection, a quiet hope that somewhere across the unimaginable gulf of space and time, someone else is listening to